The moment the data appeared on the screens of several observatories around the world, no one reacted with celebration. There was no applause, no dramatic announcement, no press release prepared in advance. Instead, there was silence. The kind of silence that only appears when scientists realize they may be looking at something that should not exist, or at least something that forces them to rethink everything they thought they understood about life in the universe. For decades, Earth had been treated as the benchmark, not because it was perfect, but because it was the only confirmed example of a life-bearing planet. Every model of habitability, every probability equation, every estimate of alien life started with a single assumption. If a planet is like Earth, life might exist. If it is less Earth-like, the chances decrease. The idea that a planet could be not just similar to Earth, but objectively better for life, sounded like science fiction, not peer-reviewed science. Yet the data kept returning the same result. This was not a claim based on a blurry image or a single telescope reading. It was a convergence of independent measurements. Orbital stability, stellar radiation levels, atmospheric chemistry, surface temperature, consistency, and long-term climate modeling all pointed in the same direction. According to the combined models, this planet had a 99.7% probability of sustaining life under known biological principles, not hypothetical exotic life, but life as we understand it. The shock came not from the number itself, but from how conservative the calculations were. Astrophysicists deliberately avoid extreme certainty. Uncertainty is built into every model. Margins of error are widened, assumptions are tested against worst-case scenarios, and confidence levels are usually expressed with caution. A probability approaching certainty is almost unheard of in planetary science, especially when dealing with a world dozens of light years away. The discovery did not begin with a search for life. It began with a routine survey. Astronomers were cataloging exoplanets around relatively quiet stars, focusing on long-term orbital behavior rather than immediate habitability. The goal was to understand how common, stable planetary systems are in the galaxy. During this process, one planet stood out immediately, not because it was Earth-sized, and not because it sat neatly in the traditional habitable zone, but because its energy balance was unusually stable. Most planets experience fluctuations. Orbital eccentricity causes seasonal extremes. Stellar flares introduce radiation spikes. Atmospheric loss alters surface conditions over time. This planet showed none of that. Year after year, simulated decades into the future, its climate remained steady. Temperature variations were minimal. Radiation exposure stayed within a narrow band. Nothing about it suggested chaos. Initially, researchers assumed there was a mistake. Instruments were recalibrated. Datasets were cross-checked with other observatories. Older observations were reanalyzed. Instead of correcting the anomaly, each verification strengthened it. The planet was not an error, it was an outlier. As more parameters were added, the picture became even more unsettling. The planet's mass suggested it could retain an atmosphere thicker than Earth's without becoming a crushing super-Earth. Gravity appeared strong enough to prevent rapid atmospheric escape, but not so strong as to hinder biological complexity. Models indicated a dense, protective atmosphere capable of distributing heat efficiently across the planet's surface. This alone would eliminate many of the extreme weather patterns that plague Earth. When atmospheric spectroscopy results arrived, skepticism turned into unease. Traces of oxygen were detected. Not in isolation, not at levels that could be dismissed as chemical noise, but alongside gases that rarely coexist without continuous replenishment. On Earth, this kind of imbalance is maintained almost exclusively by biological processes. Volcanoes and photochemical reactions cannot sustain it for long. Life can. Still, the research teams resisted the temptation to draw conclusions. Oxygen alone does not mean life. Mars once had oxygen. Venus has chemical oddities of its own. But the combination of gases, when placed within the planet's broader environmental context, shifted the probability calculations dramatically. The phrase "better than Earth" was not meant as an insult to our planet. It was a technical description. Earth sits close to the inner edge of the habitable zone. Its climate has flipped between extremes multiple times. Mass extinctions have repeatedly erased complex life. Solar activity has threatened atmospheric stability. In contrast, this planet appeared to occupy a region of long-term calm, a cosmic safe zone. Climate simulations projected billions of years of stability, both in the past and into the future. This meant life on such a planet would not need to constantly recover from global catastrophes. Evolution would have time to experiment, diversify, and stabilize. Intelligence, if it emerged, would not be repeatedly reset by asteroid impacts or runaway climate shifts. The realization spread slowly through the scientific community. Papers were circulated quietly. Conferences included closed-door sessions. No one wanted to be the first to publicly declare that Earth might not be the optimal environment for life. The implications were too large. If a planet more suitable than Earth existed, then Earth was not the standard. It was merely one example among many. This reframed the search for life entirely. For years, astronomers had focused on Earth analogues: same size, same distance from a sun-like star, same atmospheric assumptions. Now, the models suggested that the best candidates might look subtly different, slightly larger, slightly older, orbiting stars that burn more steadily and gently than our own. The probability figure of 99.7% did not emerge from optimism. It emerged from exclusion. Researchers systematically removed scenarios where life would fail. They tested atmospheric collapse, magnetic field loss, stellar radiation spikes, orbital instability, and chemical poisoning. In nearly every case, the planet's characteristics countered the threat. It was not immune to disaster, but it was resilient. Resilience is the defining feature of life-friendly worlds. Earth survives, but barely. It exists in a delicate balance, constantly pushed toward collapse by internal and external forces. This planet appeared to exist in a state of equilibrium. Not fragile, not extreme, simply stable. The emotional impact on scientists was profound. Many enter the field driven by the question of whether we are alone. Few expected the answer to challenge humanity's sense of centrality so directly. Discovering alien life would be revolutionary, but discovering a world objectively better suited for life than our own raised uncomfortable questions. If life thrives best elsewhere, then Earth is not the cosmic ideal. It is just one outcome among countless others. Media attention eventually followed, but cautiously headlines avoided absolutes. Words like possible, candidate, and potentially habitable dominated early coverage. Behind the scenes, however, confidence continued to grow. Every new observation refined the models rather than weakening them. What made this discovery truly unsettling was not the likelihood of life, but the implication of time. The planet appeared older than Earth. significantly older. If life emerged early there, it would have had hundreds of millions, possibly billions, of additional years to evolve. That span is enough to produce complexity far beyond microbial ecosystems. No evidence of intelligence was claimed. No signals were detected. But the absence of evidence was no longer reassuring. It was simply unknown. And for the first time, the unknown felt statistically crowded. The scientific community now faced a dilemma: how to communicate a discovery that undermines the quiet assumption that Earth is special without drifting into speculation or sensationalism. The answer was restraint. Let the data speak. Let the models converge. Let skepticism remain. Yet even in restraint, the conclusion was unavoidable. Somewhere in the galaxy, a planet exists that may offer life a calmer, longer, more stable home than the world humanity evolved on. Not a paradise in a poetic sense, but an environment optimized by physics and chemistry for biological continuity. This discovery did not answer the question of whether we are alone. Instead, it transformed the question entirely. The universe no longer appeared hostile, with rare pockets of survival. It appeared selective. And Earth, for the first time, seemed like a compromise rather than the masterpiece. This was only the beginning. To understand why scientists would ever describe another planet as better than Earth, the definition of habitability itself has to be stripped of emotion and familiarity. Habitability is not about beauty, comfort, or resemblance to home. It is a technical concept rooted in physics, chemistry, biology, and time. When researchers say a planet may be more habitable than Earth, they are not claiming it is paradise. They are saying it offers conditions that make life more likely to emerge, survive, and persist without interruption. For most of modern astronomy, habitability was simplified into a single idea: the habitable zone. This was the region around a star where liquid water could exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. Earth sits within this zone, so the logic followed that planets in similar zones might also host life. This framework was useful, but deeply incomplete. Liquid water is necessary for life as we know it, but it is not sufficient. Mars once had liquid water and lost it. Venus may have had oceans and became a furnace. Habitability is not a snapshot. It is a long-term condition. A planet must maintain suitable environments for hundreds of millions or billions of years for life to do more than briefly appear and disappear. This is where Earth begins to look less ideal. Earth's climate history is violent. It has oscillated between icehouse and greenhouse states. It has experienced mass extinctions that wiped out most existing species. Its atmosphere has changed dramatically over time. Its magnetic field has weakened and strengthened. Life survived these events. But survival is not the same as optimal conditions. Earth is resilient, not gentle. Scientists now evaluate habitability using a multi-dimensional framework. Surface temperature stability is one factor. Atmospheric retention is another. Stellar radiation levels matter. So does gravity, planetary mass, internal heat, magnetic shielding, chemical cycling, and orbital consistency. Even the type of star a planet orbits plays a decisive role. When these factors are applied to Earth without bias, the results are surprising. Earth scores well, but not exceptionally. It is near several thresholds. Its position in the habitable zone is closer to the inner edge than the center. A slight increase in solar output could trigger runaway warming. A slight decrease could push the planet toward global ice coverage. Earth operates with narrow margins. The newly studied planet does not. Temperature stability is one of the strongest indicators of habitability. Life can adapt to heat and cold, but rapid or extreme swings are destructive. On Earth, ice ages and warming periods have repeatedly reshaped ecosystems. While this drives evolution, it also causes mass die-offs. A planet with smaller temperature fluctuations offers life continuity rather than constant recovery. Models suggest this planet's average surface temperature remains within a narrow band across its entire orbit. Seasonal variation exists, but it is muted. This is likely due to a combination of orbital circularity, atmospheric thickness, and oceanic heat distribution. Heat does not accumulate at the equator or collapse at the poles. Energy moves efficiently. Atmospheric composition is another critical metric. Earth's atmosphere is thin enough to allow radiation penetration, yet thick enough to trap heat. It is a delicate balance. Changes in carbon dioxide levels have repeatedly destabilized climate systems. Volcanic events and biological shifts have altered atmospheric chemistry dramatically. On the other planet, simulations indicate a thicker, more stable atmosphere, not crushing, not toxic, but resilient. Such an atmosphere buffers temperature changes, shields the surface from harmful radiation, and allows chemical cycles to operate without abrupt collapse. It reduces the chance of global climate tipping points. Gravity plays a subtle but essential role. If gravity is too weak, a planet cannot hold onto its atmosphere. Solar winds strip it away, as happened to Mars. If gravity is too strong, atmospheric pressure becomes extreme, potentially limiting complex life forms and altering chemistry. Earth's gravity is adequate, but again, close to minimum thresholds. The planet in question appears slightly more massive than Earth, but not enough to be classified as a super-Earth. This increased mass strengthens atmospheric retention and may support long-term geological activity. Internal heat remains present for longer periods, driving tectonics and magnetic field generation. Plate tectonics are often overlooked in discussions of habitability, yet they are crucial. Tectonic activity recycles carbon, regulates atmospheric composition, and maintains surface diversity. Earth's plate tectonics have prevented carbon dioxide buildup and helped stabilize climate over geological timescales. Without them, Earth might resemble Venus. Models suggest this planet may have similar or even more consistent tectonic processes. Its internal heat loss is slower, meaning geological activity could persist for longer spans of time. This extends the window during which life-friendly conditions exist. Stellar behavior may be the most important factor of all. Earth orbits a relatively stable star, but our Sun is not perfectly calm. Solar flares, coronal mass ejections, and long-term luminosity increases all pose risks. Early in Earth's history, solar radiation levels were different. In the future, they will become hostile. The planet's parent star is quieter. It emits energy more steadily and produces fewer high-energy flares. This reduces radiation damage to the atmosphere and surface life. It also lowers the likelihood of atmospheric erosion. Stability at the stellar level translates directly into planetary habitability. Time is the final and often neglected metric. Habitability is meaningless if it lasts only briefly. Life requires time to emerge, diversify, and adapt. Earth became habitable relatively early, but it also experienced multiple near collapses. Intelligence emerged late, after billions of years of setbacks. This planet appears to have entered a stable, habitable state earlier and remained there longer. That extended duration dramatically increases the probability of life. Not because conditions are perfect, but because they are consistently good. Evolution thrives on consistency more than perfection. This is why the phrase "better than Earth" is scientifically valid within context. It does not mean superior in every way. It means less extreme, more stable, and less vulnerable to catastrophic resets. Earth supports life. Despite its instability, this planet may support life because of its stability. Habitability indices used by scientists assign weighted values to each factor. Temperature stability, atmospheric retention, stellar radiation, orbital dynamics, and geological activity are scored and combined. Earth performs well, but loses points due to climate volatility and proximity to critical thresholds. The other planet scores higher, not by excelling dramatically in one category, but by performing consistently well across all of them. No single weakness dominates its profile. It lacks the dramatic extremes that characterize Earth's history. This reframing challenges deeply held assumptions. Humans evolved under unstable conditions and adapted accordingly. Our narratives celebrate survival against adversity. But biology does not prefer adversity. It tolerates it. Given a choice, life favors environments that do not constantly threaten extinction. A planet that avoids global catastrophes allows ecosystems to mature. Complexity increases. Niches diversify. Evolutionary experimentation accelerates. Intelligence, if it emerges, has time to persist rather than restart. This does not mean Earth is rare or doomed. It means Earth is not the upper bound of habitability. It is not the template the universe strives to reproduce. It is one configuration among many possible ones. Understanding this distinction is essential. The discovery is not about diminishing Earth's value. It is about expanding our understanding of where life can thrive best. When scientists say a planet may be better than Earth, they are not making a philosophical statement, they are making a statistical one. And statistically, Earth may be good, but not optimal. This realization forces a shift in how future searches are conducted. Instead of looking only for Earth twins, scientists now look for Earth improvements, worlds that sit deeper in habitable zones, worlds orbiting calmer stars, worlds with thicker atmospheres and longer geological lifespans. The universe may not be waiting to copy Earth. It may be producing something quieter, older, and more stable. And in that silence, life may flourish far more easily than it ever did here. The number 99.7% did not appear as a headline first. It appeared as a variable buried deep inside simulation outputs, surrounded by caveats, confidence intervals, and assumptions clearly labeled in footnotes. Scientists do not announce certainty lightly, especially when the subject is life beyond Earth. So when this probability emerged, it was not treated as a conclusion, but as a problem, a number that demanded explanation rather than acceptance. Probability in astrobiology does not work the way it does in everyday life. It is not a prediction that something will happen tomorrow, nor a claim that life has already been observed. It is a statistical assessment based on exclusion. Scientists ask not why life should exist, but under what conditions life would fail. When those failure pathways are systematically removed, what remains is probability. The 99.7% figure represents the likelihood that life could arise and persist on this planet given known biological and physical constraints. It is not based on optimism, it is based on redundancy. The planet appears to meet multiple independent criteria for habitability simultaneously. If one system fails, another compensates. This overlap dramatically increases survivability. The process begins with baseline requirements: liquid water, a stable energy source, and essential chemical elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are non-negotiable for life as we understand it. The planet satisfies these conditions comfortably, but many planets do. This alone does not produce a high probability. The next layer involves environmental continuity. Life does not emerge instantly. It requires time, chemical gradients, and repeated cycles of stability. Scientists simulate billions of years of planetary history, testing whether conditions remain within survivable limits on Earth. These simulations reveal frequent disruptions. Ice ages, volcanic winters, asteroid impacts, and atmospheric shifts repeatedly push ecosystems to the edge. On this planet, the simulations tell a different story. Disruptions occur, but they are smaller, less frequent, less global. The planet's systems absorb shocks rather than amplify them. Climate feedback loops stabilize rather than spiral. This dramatically reduces extinction risk at early stages of life, when organisms are most vulnerable. Another critical factor is energy balance. Life requires energy, but too much energy is destructive. High radiation levels damage DNA. Intense stellar flares strip atmospheres. Excessive ultraviolet exposure sterilizes surfaces. The planet's parent star emits energy steadily, with fewer extreme events. Models show radiation levels remaining within biologically tolerable ranges for extended periods. This matters because early life is fragile. Before protective mechanisms evolve, radiation can easily erase progress. Earth's early life survived in part because it was shielded by oceans. A planet that offers surface-level protection allows life to diversify more rapidly, that accelerates biological complexity. Chemical disequilibrium plays a central role in the probability calculation. Life is not defined by specific molecules, but by processes that push chemistry away from equilibrium. On Earth, oxygen and methane coexist in the atmosphere only because life continuously produces them. Without biology, they would react and disappear. Spectroscopic data from this planet suggests the presence of multiple gases that should not coexist under purely abiotic conditions. Individually, each gas could be explained by non-biological processes. Together, their persistence becomes statistically unlikely without continuous replenishment. When models test non-biological explanations, they fail to maintain stability over long timescales. This does not prove life exists, but it dramatically increases the probability that life could exist. The distinction is subtle but important. Science does not claim certainty without direct observation. Instead, it measures how implausible non-life explanations become. Planetary mass and gravity introduce another layer of resilience. The planet's slightly higher mass allows it to retain a thick atmosphere and sustain internal heat. This supports a long-lived magnetic field. Magnetic fields protect atmospheres from stellar winds. Without them, planets slowly bleed their gases into space. Mars lost its magnetic field early and paid the price. Its atmosphere thinned, its water evaporated or froze, and its surface became hostile. This planet's magnetic field appears stronger and longer lived. Models suggest it could persist for billions of years, shielding surface environments from radiation. Time again becomes a multiplier. Each additional billion years of stability increases the chance that life not only emerges, but survives long enough to become detectable. Probability compounds. Early life leads to complex life. Complex life increases chemical signatures. Chemical signatures persist and strengthen. The 99.7% figure emerges after thousands of simulated histories. Scientists run models where parameters are altered slightly. What if the star becomes more active? What if volcanic output increases? What if atmospheric composition shifts? In most scenarios, life remains viable. Only extreme deviations lead to collapse. This robustness is rare. Earth's habitability collapses in a much larger fraction of simulations. Slight changes push it toward runaway greenhouse states or global glaciation. Earth survives because it exists in a dynamic balance, not because it is inherently stable. Another factor is the planet's orbital dynamics. Its orbit is nearly circular. Eccentric orbits create extreme seasons. Planets swing closer and farther from their stars, experiencing temperature extremes. This planet's orbit minimizes those swings. Energy input remains consistent. Climate systems remain predictable. Predictability favors life. It allows ecosystems to establish long-term patterns. Nutrient cycles stabilize. Food webs diversify. Extinction events become local rather than global. Probability increases not because conditions are perfect, but because they are dependable. Statistical models also account for false positives. Scientists intentionally inflate error margins. They assume worst-case uncertainties in measurements. Even under these conservative assumptions, the probability remains above 95%. Reaching 99.7% requires stacking conservative models on top of conservative assumptions. This is why the number drew attention. It is also why scientists hesitate to publicize it. Probability does not translate cleanly into public understanding. A 99.7% chance of life does not mean life has been observed. It means that, given what we know, life is the most parsimonious explanation for the planet's properties. The calculation also reflects selection bias correction. Astronomers know they observe planets that are easier to detect. Large planets, close orbits, bright stars. They correct for this by adjusting probability distributions. Even after correction, the planet remains an extreme outlier in habitability metrics. One of the most important aspects of the calculation is independence. Each habitability factor is weighted based on how independent it is from others. Atmospheric stability is not counted twice if it depends on gravity. Stellar stability is treated separately. Geological activity is considered semi-independent. The overlap strengthens confidence. If habitability relied on a single fragile condition, probability would remain low. But this planet's habitability arises from multiple reinforcing systems. When one stabilizing factor weakens, another compensates. This redundancy mirrors robust biological systems on Earth, where life persists despite localized failures. The final probability emerges from Bayesian frameworks. Prior assumptions about life frequency are updated based on new evidence. As evidence accumulates, probabilities shift. In this case, they shifted sharply upward, not because of belief, but because alternative explanations became less plausible. Scientists remain cautious in their language. They emphasize that probability is not confirmation, but internally the shift is profound. The question is no longer whether such a planet could host life. The question is whether it would be surprising if it did not. This reframing changes how discoveries are interpreted. Absence of direct evidence becomes less meaningful when probability is high. Silence does not imply emptiness. It implies distance, limitation, and technological constraint. The 99.7% figure also forces reflection on humanity's expectations. For decades, life elsewhere was treated as rare. The universe appeared hostile, with Earth as an exception. Now, the data suggests the opposite. Earth may be unusually chaotic. Life may prefer calmer worlds. This does not diminish the value of human existence. It contextualizes it. We evolved under pressure. We adapted to instability. But life elsewhere may have evolved under gentler conditions, with fewer resets and longer continuity. Probability does not tell us what that life looks like. It does not tell us whether it is microbial or complex. It does not tell us whether intelligence emerged. It tells us only that, given the rules of chemistry and physics, life has had every opportunity to succeed. And opportunity, in biology, is everything. The number 99.7% is not a declaration. It is a warning to our assumptions, a reminder that certainty about uniqueness was never justified. The universe does not owe us exclusivity. As models continue to refine and telescopes improve, this number may change. It may drop slightly. It may rise. But the threshold has already been crossed. The probability is no longer marginal. It is overwhelming. And with that realization, the search for life moves from hopeful speculation to statistical expectation. This planet is not proof that we are not alone. It is evidence that being alone would be the greater anomaly. Location matters more than distance, and this planet's position in the universe is one of the quiet reasons scientists became increasingly confident in its potential for life. When people hear that a planet is dozens or even hundreds of light years away, the number sounds abstract, almost meaningless. Distance alone tells us very little about habitability. What truly matters is where a planet sits within its local cosmic environment and how that environment behaves over immense stretches of time. This planet does not orbit near the crowded core of its galaxy. It resides in a relatively calm region, far from the dense stellar traffic and violent gravitational interactions that dominate galactic centers. Near those regions, stars are packed tightly together. Supernovae are more frequent, and radiation levels spike unpredictably. Planetary systems are often destabilized by passing stars. For life, these neighborhoods are hostile. Earth itself benefits from being located in a quieter spiral arm away from frequent cosmic catastrophes. This planet occupies a similarly calm region, but models suggest its location may be even more favorable. Nearby stars are spaced farther apart. Gravitational disturbances are rare. The chance of a close stellar encounter disrupting planetary orbits is extremely low over billions of years. This stability matters because habitability is cumulative. A planet can have perfect conditions today and still be lifeless if it was sterilized repeatedly in the past. Gamma-ray bursts, nearby supernovae, and intense cosmic radiation events can wipe out surface life or prevent it from ever gaining a foothold. The farther a planet is from these dangers, the higher its long-term survival probability. Astronomers assess galactic habitability by mapping radiation density, star formation rates, and stellar lifespans. Regions with frequent massive star formation are dangerous. Massive stars burn fast and die violently, producing supernovae that flood surrounding space with lethal radiation. Calmer regions dominated by long-lived stars provide safer environments. This planet's neighborhood is dominated by older, stable stars. These stars burn steadily and quietly, emitting predictable energy over billions of years. Their longevity provides extended windows for life to develop. The planet is not racing against cosmic time. It exists in a slow, patient region of the galaxy. Its distance from its host star is also crucial, but again, not in the simplistic sense of being in a habitable zone. What matters is how energy is delivered over time. This planet receives a consistent energy flow with minimal fluctuation. Its orbit keeps it well within a region where liquid water can persist without extreme seasonal changes. Earth's orbit is slightly elliptical. This contributes to seasonal variation, which life has adapted to, but stronger orbital eccentricity would cause dramatic temperature swings. Many exoplanets experience far greater eccentricity, making long-term surface stability difficult. This planet's orbit is almost circular. The energy it receives does not spike or collapse throughout its year. Even more important is orbital isolation. Some planets exist in tightly packed systems where gravitational interactions between neighboring planets cause orbital wobble. Over time, these interactions can destabilize climates, tilt axes unpredictably, or eject planets entirely. This planet appears to exist in a well-spaced system with minimal interference from neighbors. This isolation creates a kind of gravitational quiet. Axial tilt remains stable. Seasons remain predictable. Climate systems have time to equilibrate. Life does not need to constantly adapt to chaotic changes in sunlight distribution or gravitational stress. Astronomers also consider vertical position within the galaxy. Planets that oscillate above and below the galactic plane can experience varying radiation exposure. The galactic plane contains higher densities of gas, dust, and energetic events. A stable vertical orbit reduces exposure to these hazards. Models indicate that this planet's stellar system maintains a relatively constant position relative to the galactic plane. It does not plunge through dense regions repeatedly. This further reduces long-term radiation risk. Distance from Earth introduces observational challenges, but does not diminish habitability. In fact, many planets closer to us reside in less favorable regions. Proximity is irrelevant to biology. Life does not care how far away it is from us. It cares about stability, energy, and chemistry. The planet's star itself plays a central role in location-based habitability. Its spectral type determines how energy is distributed. Stars cooler than the Sun emit more energy in infrared wavelengths, which interact differently with atmospheres. This can enhance greenhouse stability without excessive surface radiation damage. This star emits fewer high-energy ultraviolet bursts. Ultraviolet radiation can break down complex molecules essential for life. While some ultraviolet exposure may aid prebiotic chemistry, excess radiation is destructive. This planet's location relative to its star balances these effects. Stellar flares are another threat. Many stars, particularly smaller ones, produce violent flares that can strip atmospheres and irradiate surfaces. This planet-star exhibits low flare activity. Long-term observations show minimal extreme events. This reduces atmospheric erosion and preserves surface conditions. Location also influences the availability of heavy elements. Planets formed from material enriched by previous generations of stars. Too early in the universe's history, heavy elements were scarce. Too close to regions of intense star formation, heavy element distribution can be chaotic. This planet formed in an era and region where essential elements were abundant and evenly distributed. This ensures access to elements needed for complex chemistry. Carbon, oxygen, nitrogen, phosphorus, and trace metals are present in sufficient quantities. Without these, life, as we understand it, cannot develop. The planet's formation environment appears chemically favorable. Another overlooked aspect of location is the absence of large nearby radiation sources such as pulsars or black hole jets. These phenomena emit focused beams of high-energy radiation capable of sterilizing planets across vast distances. Surveys show no such threats in this planet's vicinity. Over geological timescales, these factors compound. A slightly safer region does not matter much. Over 1 million years, over 1 billion years, it matters enormously. Each avoided catastrophe increases the chance that early life survives long enough to diversify. Earth has been lucky. Several mass extinction events narrowly avoided complete sterilization. A slightly closer supernova, a slightly larger asteroid, or a more prolonged volcanic winter could have ended complex life permanently. Earth survived by chance as much as by resilience. This planet appears to rely less on chance. Its location reduces exposure to low probability but high impact events. It exists in a cosmic environment that is simply quieter. Quiet does not mean inactive. Geological and biological processes still occur. Evolution still experiments. But the background noise of the universe is lower. Fewer resets occur. Continuity becomes the dominant theme. This has profound implications for the likelihood of complex life. Complexity requires time uninterrupted by catastrophe. Nervous systems, multicellular organization, and ecological networks take hundreds of millions of years to develop. Frequent global disruptions prevent this. A planet located in a calmer galactic region offers life the gift of time. Not just time to exist, but time to stabilize, diversify, and potentially become self-aware. Location also affects detection. A planet in a less crowded stellar field is easier to study. Signals are clearer. Data is cleaner. This allowed scientists to refine models with higher confidence. Observational clarity reinforced theoretical conclusions. As telescopes improve, location will become a primary filter in the search for life. Astronomers will prioritize planets not just in habitable zones, but in habitable neighborhoods. The universe is not uniformly friendly. Some regions are biological deserts. Others may be biological sanctuaries. This planet appears to reside in such a sanctuary. Its distance from Earth does not isolate it from life. It isolates it from danger. It sits far from cosmic violence, bathed in steady starlight, orbiting calmly through a region that changes slowly and predictably. When scientists evaluate habitability, they no longer ask only whether a planet can host life. They ask whether it can protect life from the universe itself. In that respect, location is not a detail. It is a shield. This planet's location may be one of its greatest strengths, not because it is special, but because it avoids extremes. It does not sit at the edge of danger. It sits in the middle of calm. And in the vast, restless structure of the galaxy, calm may be the rarest and most valuable resource of all. This realization shifts perspective. Earth's place in the cosmos is no longer the default. It is one possibility among many. Some worlds may have been given quieter skies, gentler radiation, and longer peace. In such places, life does not fight the universe. It simply grows. The star a planet orbits determines far more than how bright its sky appears. It controls energy flow, radiation exposure, atmospheric survival, and the long-term fate of every biological process on the surface. When scientists began examining the parent star of this planet, they quickly realized that its calm nature might be one of the most important reasons the planet appears so exceptionally habitable. For a long time, Earth's sun was treated as an ideal reference. It is stable, long-lived, and produces a relatively consistent energy output. Without it, life on Earth would not exist. But ideal does not mean optimal. When compared to other stars across the galaxy, the Sun reveals weaknesses that are easy to overlook when it is the only example we know. Our Sun is a middle-aged star in a dynamic phase of its life. It emits solar flares, coronal mass ejections, and long-term increases in luminosity over billions of years. Its energy output slowly rises. This gradual brightening will eventually render Earth uninhabitable long before the Sun becomes a red giant. Life on Earth exists within a finite window. The planet in question orbits a star that behaves differently. This star is slightly smaller and cooler than the Sun, but not dramatically so. It does not fall into the category of highly active red dwarfs that bombard nearby planets with intense flares. Instead, it occupies a quieter spectral class where energy output is steady and predictable. Its radiation environment is gentler and its long-term evolution is slower. Stellar stability is critical for life. Frequent flares can strip planetary atmospheres, especially if the planet orbits close to the star. They can also damage biological molecules and disrupt chemical processes essential for life. On Earth, our magnetic field and atmosphere shield us from much of this activity. Even so, solar storms occasionally interfere with technology and alter atmospheric chemistry. The star this planet orbits produces fewer extreme events. Long-term monitoring shows a low frequency of high-energy flares. When flares do occur, they are weaker than those commonly observed from many stars of similar size. This reduces atmospheric erosion and surface radiation exposure. This calmness extends beyond short-term behavior. Stellar variability over millions of years can destabilize planetary climates. Some stars experience cycles of activity that dramatically alter energy output. Others evolve rapidly, changing luminosity in ways that push planets out of habitable conditions. This star evolves slowly. Its energy output changes at a reduced rate compared to the Sun. This means the planet's habitable window is longer. Life has more time not just to emerge, but to persist without being forced into extreme adaptation or extinction. Another important factor is spectral output. Stars emit energy across a range of wavelengths. Ultraviolet radiation is particularly damaging to biological molecules. While some ultraviolet exposure may play a role in early chemical evolution, excessive amounts break down DNA and proteins. This star emits a lower proportion of high-energy ultraviolet radiation than the Sun. More of its energy is delivered in wavelengths that penetrate atmospheres without destroying complex molecules. This creates a surface environment where chemistry can proceed without constant radiation damage. For early life, this is crucial. Before protective mechanisms such as ozone layers develop, life is vulnerable. A calmer radiation environment increases the probability that early biological systems survive long enough to stabilize and diversify. Stellar winds also play a role. Streams of charged particles can erode planetary atmospheres over time. Mars lost much of its atmosphere because it lacked sufficient magnetic shielding against solar wind. Even a planet with a magnetic field can suffer gradual atmospheric loss if stellar winds are intense. Observations suggest that this star produces weaker stellar winds than the Sun. Combined with the planet's stronger magnetic field, this dramatically reduces atmospheric loss. Gases essential for climate regulation and biology remain trapped over geological timescales. The relationship between star and planet is not passive. It is a dynamic interaction. The star sets the boundary conditions, but the planet responds. A calm star allows the planet's own stabilizing systems to dominate. Climate feedback loops operate smoothly. Chemical cycles reach equilibrium. In contrast, a violent star forces constant adjustment. Atmospheres thicken or thin. Surface conditions oscillate. Life adapts or dies. Earth's history reflects this struggle. Solar variability has influenced climate patterns and atmospheric chemistry repeatedly. The planet orbiting this calmer star avoids much of that struggle. Distance also matters. Because the star is cooler, the planet orbits slightly closer than Earth does to the Sun. Normally, close orbits raise concerns about tidal locking, where one side of a planet permanently faces the star. Tidal locking can create extreme temperature contrasts. However, this planet's mass and orbital characteristics prevent full tidal locking. Its rotation remains sufficient to distribute heat globally. Day and night cycles exist. This maintains atmospheric circulation and prevents permanent freezing or overheating on either side. The balance is delicate, but it appears stable. Simulations show effective heat redistribution via winds and oceans. Temperature gradients remain moderate. This is another example of how multiple factors align to support habitability. The star's longevity is perhaps its greatest gift. Smaller, cooler stars burn fuel more slowly. They can remain stable for tens of billions of years. While the Sun has a total lifespan of about 10 billion years, this star's lifespan may be several times longer. This means the planet's habitable era is extended far into the future. Life does not face an impending stellar deadline. Evolution can proceed without the looming threat of stellar aging. Time changes everything. With more time, complexity increases. Ecosystems stabilize. Intelligence, if it emerges, has a greater chance to persist rather than vanish quickly. Scientists refer to this as temporal habitability. It is not enough for a planet to be habitable now. It must remain habitable long enough for life to become detectable. Earth only recently developed a technological species. If the Sun's lifespan were shorter, humanity might never have emerged. This planet's star provides a longer runway. Another subtle factor is stellar metallicity. This refers to the abundance of elements heavier than hydrogen and helium in a star. Stars with higher metallicity tend to form planets with richer chemical inventories. These elements are essential for rocky planet formation and complex chemistry. This star has a favorable metallicity. It formed after multiple generations of stellar evolution enriched its region of the galaxy. The resulting planet inherited a diverse mix of elements. This supports complex geology and biochemistry. The star's calmness also affects detectability. Stable stars produce cleaner observational data. Fewer flares mean fewer distortions in spectral readings. This allowed scientists to analyze the planet's atmosphere with higher confidence. Clearer data reinforced conclusions about habitability. This is an important feedback loop. Calmer stars not only create better environments for life, they also make life easier to detect. This may bias our discoveries toward planets orbiting such stars, but it also highlights where life is most likely to persist. Earth's sun is not hostile. It is simply average. It provides just enough stability for life to survive. The star this planet orbits appears to do slightly better. It removes some of the hazards without eliminating the energy needed for life. This does not mean that life cannot exist around more active stars. It means that the probability is lower. Stability increases probability. Calm stars create better statistical conditions for biology. When scientists factor stellar behavior into habitability models, the numbers shift significantly. Planets that would otherwise seem marginal become promising if their stars are quiet. Planets that appear ideal can become hostile if their stars are violent. In this case, the star amplifies the planet's strengths. It does not introduce new risks. It acts as a steady energy source rather than a disruptive force. This reframes the search for life. Instead of asking which planets resemble Earth, scientists increasingly ask which stars resemble the calm ideal. Earth may be an exception not because it hosts life, but because life survived despite a more active stellar environment. In a galaxy filled with stars, only a fraction provide this level of calm. Among those, only a fraction host rocky planets in stable orbits. Among those, only a fraction retain atmospheres and liquid water. This planet passed each filter. The star it orbits is not famous. It is not bright or dramatic. It does not dominate its region of space. It simply burns quietly, day after day, for billions of years. For life, this quiet persistence may be the greatest gift a star can offer. When scientists say this planet may be better than Earth, they are not only talking about the planet itself, they are talking about the system. A world does not exist in isolation. It is shaped by its star. And in this case, the star appears to be exactly what life prefers. Not brilliant, not violent, just steady. A planet's orbit is not merely a path through space. It is a long-term contract with gravity, energy, and time. Even small irregularities in orbital behavior can destabilize climates, disrupt chemical cycles, and erase biological progress. When scientists examined the orbital mechanics of this planet, they found something rare, near perfect consistency. Most planets do not move in clean circles. Their orbits stretch and compress, bringing them closer to and farther from their stars over the course of a year. This eccentricity creates seasonal extremes. Mild eccentricity, like Earth's, produces manageable variation. High eccentricity can be catastrophic, swinging planets between scorching heat and deep freeze. This planet's orbit is almost circular. Energy input remains remarkably constant throughout its year. Temperature models show minimal deviation between closest and farthest points from the star. This alone reduces climate stress dramatically. But orbital shape is only the beginning. Many planetary systems are crowded. Planets tug on one another gravitationally, causing long-term orbital wobble. These interactions can alter axial tilt, shift climates, or even eject planets from their systems. Earth benefits from a relatively orderly solar system, but even here, gravitational resonances have influenced climate cycles. This planet appears to exist in a dynamically quiet system. Neighboring planets, if present, are well spaced. Their gravitational influence is weak and stable. Long-term simulations show minimal orbital drift over billions of years. This is an extraordinary level of predictability. Predictability is essential for life. Ecosystems rely on regular cycles, nutrient flows, reproduction, migration, and evolutionary pressures all depend on consistent environmental rhythms. When those rhythms are disrupted, extinction risk rises. Earth's axial tilt fluctuates over time. These changes drive ice ages and interglacial periods. While life survives, complexity suffers. Each global shift resets ecosystems. A planet with a stable tilt avoids these repeated disruptions. Models indicate that this planet's axial tilt is stabilized, likely by a combination of mass distribution and possibly the presence of a large moon. A stable tilt produces consistent seasons or potentially very mild seasonal variation. Neither extreme summer nor extreme winter dominates. Seasonal moderation matters. Extreme seasons limit biodiversity. Organisms must invest energy in survival rather than growth. Moderate, predictable seasons allow ecosystems to specialize and diversify. Tidal forces also shape habitability. Planets orbiting close to their stars can become tidally locked, with one hemisphere permanently facing the star. This creates a permanent day side and night side. Temperature differences become extreme. Atmospheric circulation can collapse. This planet avoids full tidal locking. Its orbital distance, rotational speed, and internal structure allow it to maintain a rotating day-night cycle. This distributes heat across the surface and prevents permanent climate zones. Tidal interactions do exist, but they are gentle. Gentle tidal forces can actually benefit habitability by driving internal heating and supporting geological activity. Earth's moon plays this role, contributing to tides and possibly stabilizing axial tilt. This planet may experience similar benefits without destructive tidal stress. Orbital stability also affects atmospheric chemistry. Rapid changes in energy input can disrupt chemical equilibrium. Greenhouse gases may accumulate or dissipate too quickly. Climate feedback loops may overshoot. On this planet, slow, steady energy input allows chemical cycles to regulate climate effectively. Carbon cycling remains balanced. Oceans absorb and release heat gradually. Runaway greenhouse or snowball states become unlikely. Scientists ran extreme simulations to test orbital vulnerability. They introduced hypothetical perturbations, nearby passing stars, increased planetary mass in neighbors, minor changes in stellar mass. In most scenarios, the planet's orbit remains stable. Only extreme, unlikely events cause collapse. Earth does not perform as well under similar tests. Our orbit and tilt are more sensitive to perturbation. We have survived because catastrophic perturbations have not occurred, not because our system is inherently resistant. This planet appears inherently resistant. The duration of stability is critical. Short-term stability does not matter if long-term chaos follows. Models extending tens of billions of years show this planet remaining within habitable parameters far longer than Earth. This means life has not only time to arise, but time to endure. Intelligence, if it evolves, is not racing against orbital chaos. Another subtle factor is resonance avoidance. Some planets fall into orbital resonances that amplify perturbations over time. This can lead to dramatic shifts in orbit or rotation. This planet avoids strong resonances. Its orbital period does not align destructively with neighbors. This reduces long-term risk. Stability compounds over time. Each avoided resonance reduces the chance of eventual destabilization. Orbital inclination also matters. Planets with high inclination relative to the system plane experience varying radiation exposure and gravitational stress. This planet's inclination is low. Its path is aligned with the system's plane. Energy exposure remains consistent. The concept of eternal stability does not imply absolute permanence. No system is immune to change. Stars evolve. Galaxies shift. Randomness exists. But in comparative terms, this planet approaches the upper limit of orbital predictability. Scientists sometimes describe this as a low-entropy orbit. Energy flows are smooth. Disruptions are rare. The system resists chaos. For life, this is invaluable. Early life requires millions of years of calm to establish metabolic pathways. Complex life requires hundreds of millions more to diversify. Intelligence requires billions. Any global disruption can reset progress to zero. Earth experienced multiple resets. Mass extinctions delayed complexity repeatedly. Yet, life persisted. On this planet, fewer resets mean faster cumulative progress. This does not guarantee intelligence. It increases probability. Evolution is not directed, but stability removes one of its greatest obstacles. Orbital stability also influences ocean dynamics. Stable rotation and energy input support long-term ocean circulation patterns. These patterns distribute nutrients and regulate climate. Unstable orbits disrupt circulation, leading to stagnation or extreme currents. Models suggest this planet maintains steady ocean circulation. Heat and nutrients move efficiently. Ecosystems can develop across latitudes rather than being confined to narrow bands. This supports biodiversity. Biodiversity increases resilience. Resilient ecosystems survive local disturbances without global collapse. Another consequence of stability is predictability of day length. Extreme changes in rotation rate can alter atmospheric dynamics. This planet's rotation appears stable. Day length remains consistent. Atmospheric circulation patterns remain steady. This matters for photosynthesis. Plants and photosynthetic organisms depend on regular light cycles. Irregular or extreme cycles limit productivity. Everything about this planet's orbit suggests moderation, not perfection, but balance. Not static, but steady. When scientists compare habitability, they often focus on dramatic features: oceans, atmospheres, temperatures. Orbit rarely captures public attention, yet orbit underpins all of these. A perfect atmosphere means little if orbit destabilizes climate. Liquid water evaporates or freezes if energy input swings wildly. Life cannot adapt to unpredictability at planetary scales. This planet offers predictability, not as a momentary state, but as a long-term condition. The phrase eternal stability is not poetic exaggeration. It is a statistical description. Within modeled timescales relevant to biological evolution, the planet remains stable. Earth is habitable in spite of its orbital dynamics. This planet may be habitable because of them. This distinction reshapes our understanding of life in the universe. Perhaps life does not flourish where conditions are barely sufficient. Perhaps it flourishes where conditions are boring. No dramatic seasons, no violent orbital shifts, no existential cosmic threats arriving without warning. Just a steady rhythm of day and night, year after year, billion after billion. In such a rhythm, life does not struggle to survive. It has the freedom to become something more. This orbital calm may be one of the strongest reasons scientists believe this planet is not merely habitable, but exceptionally so. It is not fighting gravity. It is in harmony with it. Water is often treated as a simple checkbox in the search for life. If liquid water exists, a planet is labeled promising. If it does not, the planet is dismissed. This binary thinking hides a deeper truth. Water is not just a requirement for life. It is an environmental regulator, a chemical medium, and a planetary stabilizer. The way water exists on a planet matters as much as its presence. Earth is sometimes called the ocean planet, yet only a small fraction of its water actively participates in climate regulation and biological processes. Most of Earth's water is locked away in deep oceans or frozen in ice. Distribution is uneven. Vast deserts exist alongside flooded regions. Climate systems struggle to balance this unevenness. The planet under study presents a different picture. Models suggest that water on this planet is abundant, but more importantly, evenly distributed. Rather than being confined to deep basins or polar ice caps, liquid water likely covers large portions of the surface in interconnected systems. Shallow seas, wide continental shelves, and extensive inland bodies of water dominate the landscape. This configuration is not accidental. It arises from a combination of gravity, topography, and atmospheric pressure. Slightly higher gravity allows water to spread more evenly rather than pooling into extreme depths. A thicker atmosphere reduces evaporation extremes. Moderate surface temperatures prevent permanent ice caps from forming too easily. Why does this matter for life? Life emerges most readily in shallow, chemically rich environments. On Earth, the earliest life likely appeared in shallow seas, tidal zones, or hydrothermal regions where energy and nutrients were concentrated. Deep oceans are vast, but relatively uniform. They are stable, but slow. Shallow environments are dynamic. They encourage chemical complexity. This planet appears to maximize those dynamic zones. Instead of a few narrow coastlines, it may host thousands of kilometers of shallow water environments. These regions experience gentle tidal mixing, nutrient recycling, and stable temperatures. They are ideal for prebiotic chemistry and early biological systems. Scientists also consider water cycling. On Earth, water cycles between ocean, atmosphere, ice, and land. This cycle regulates temperature, but also introduces volatility. Ice ages lock water away. Melting releases it suddenly. Sea levels rise and fall dramatically, reshaping ecosystems. On this planet, water cycling appears less extreme. Limited polar freezing means fewer dramatic sea level changes. Water remains accessible to ecosystems over long timescales. This continuity reduces ecological disruption. Another critical factor is salinity. Earth's oceans are saline, which influences biological chemistry. Freshwater environments exist, but they are often isolated. Transitions between saltwater and freshwater environments pose challenges for organisms. Models suggest that this planet's water chemistry may be more varied and more interconnected. Salinity gradients exist, but they are gradual. This allows life to adapt across environments rather than being trapped in narrow ecological niches. The presence of extensive shallow seas also enhances climate stability. Water has a high heat capacity. It absorbs and releases energy slowly. This buffers temperature changes. A planet with widespread surface water resists rapid warming and cooling. Earth benefits from this effect, but uneven water distribution limits it. Deserts heat quickly. Ice reflects sunlight excessively. This planet's water coverage moderates these extremes. Scientists also examine the likelihood of subsurface water. Even if surface conditions become temporarily hostile, subsurface water can shelter life. Earth hosts vast underground aquifers and deep ocean ecosystems. These act as biological refuges during surface catastrophes. This planet's internal heat and pressure conditions suggest widespread subsurface water systems. Life would have multiple refuges. Extinction becomes less likely because not all habitats are exposed to the same threats. One concern with water-rich planets is dilution. If water coverage is too extensive, essential minerals may become scarce. Life requires access to nutrients delivered by erosion and geological activity. A planet entirely covered by deep oceans may lack sufficient nutrient cycling. This planet appears to avoid that trap. Its continents are not submerged entirely. Land masses exist. Erosion feeds minerals into shallow seas. Tectonic activity replenishes nutrients. Water and rock interact continuously. This interaction is vital. It drives chemical cycles that support metabolism. Without it, life stagnates. Scientists also consider the role of water in atmospheric chemistry. Water vapor is a powerful greenhouse gas. Too much can lead to runaway warming. Too little leads to global freezing. Balance is essential. This planet's atmosphere appears to regulate water vapor effectively. Cloud formation reflects excess radiation. Precipitation distributes water evenly. Humidity remains within stable bounds. Climate models show no tendency toward runaway greenhouse states driven by water vapor feedback. Earth has narrowly avoided such states in the past. Venus did not. Another subtle advantage is reduced weather violence. Extreme storms arise from sharp temperature contrasts and unstable atmospheric dynamics. Widespread water coverage smooths these contrasts. Storms still occur, but they are less destructive. Ecosystems are disturbed less frequently. This increases biological continuity. Fewer ecosystems are wiped out by hurricanes or prolonged droughts. Recovery becomes faster. Biodiversity increases. Photosynthesis also benefits. Shallow water allows sunlight to penetrate. Photosynthetic organisms can thrive not only on land, but throughout coastal and inland seas. This increases global biological productivity. Higher productivity supports more complex food webs. Oxygen levels rise more steadily. Atmospheric composition stabilizes. Oxygen itself is a double-edged sword. It enables complex life, but can also drive oxidative damage. Stable oxygen production and consumption prevent extreme fluctuations. This planet's water-rich environments may support smoother oxygen regulation. Scientists have long debated whether Earth's water distribution is optimal or merely sufficient. Evidence increasingly suggests it is sufficient. This planet may approach something closer to optimal. Water also acts as a solvent for chemistry. The more stable and accessible water is, the more likely complex organic molecules can form and persist. Repeated wet-dry cycles in shallow environments concentrate chemicals and drive reactions. This planet offers those cycles without excessive disruption. Some models even suggest that life could emerge independently in multiple locations on such a planet. Parallel origins increase resilience. Extinction of one lineage does not eliminate life entirely. On Earth, life may have originated in a limited number of environments. This made early life vulnerable. On this planet, origin points may be numerous. This raises an unsettling possibility. Life there may not only exist, but be widespread. Microbial ecosystems could blanket shallow seas and subsurface aquifers. Chemical signatures would accumulate more strongly. This would explain why atmospheric signals appear so persistent. Life is not confined to a few niches. It is distributed. Water also influences planetary albedo. Reflective ice and clouds affect how much energy a planet absorbs. Balanced water coverage prevents excessive reflection or absorption. Energy budgets stabilize. The planet's water systems likely interact closely with its geology. Hydrothermal vents may be widespread. These environments provide chemical energy independent of sunlight. Life on Earth thrives around such vents. They may have played a role in life's origin. This planet's internal heat suggests abundant hydrothermal activity. Combined with shallow seas, this creates a rich chemical landscape. Critically, water does not exist in isolation. It interacts with every other habitability factor: atmosphere, orbit, star, geology. On this planet, those interactions appear synergistic rather than antagonistic. Earth's water systems often amplify instability. Ice albedo feedback intensifies cooling, evaporation intensifies warming. This planet's systems dampen extremes. Scientists sometimes refer to this as hydrological buffering. The planet resists climatic swings because water redistributes energy efficiently. This buffering may be one of the reasons the planet avoided snowball states or runaway greenhouse phases. Life did not need to survive global freezes or global boiling. It evolved in continuity. This continuity matters more than abundance. A planet with less water but stable distribution may outperform a planet with more water but chaotic cycling. In this case, the planet appears to have both abundance and stability. This challenges a common misconception. More water does not automatically mean better habitability. But the right kind of water distribution does. The planet's water world characteristics do not drown life, they nurture it. Scientists remain cautious. Direct imaging of surface water is limited. Much of this analysis relies on indirect data and modeling, but the convergence of evidence is compelling. When water distribution is added to other favorable factors, habitability probability increases significantly. Water does not carry the burden alone. It is part of a network of stabilizing influences. Earth's oceans saved life many times, but they also isolated it. Deep oceans slowed chemical cycling. Extreme land-water imbalance created deserts and ice caps. This planet may have avoided those extremes. If life exists there, it likely experienced fewer bottlenecks, fewer near extinctions, fewer resets. This could have profound consequences for biological complexity. Ecosystems mature when they are not repeatedly destroyed. Intelligence, if it arises, benefits from stable environments that reward long-term adaptation. Water is often romanticized in the search for life. Oceans, rivers, rain. But in science, romance gives way to systems. This planet's water systems appear to function as a stabilizing engine rather than a destabilizing force. They regulate temperature, distribute nutrients, shelter life, drive chemistry. In that sense, water on this planet is not just present, it is working. And when water works in harmony with atmosphere, orbit, and star, life does not merely survive, it thrives. An atmosphere is more than a layer of gas surrounding a planet. It is a chemical fingerprint, a climate regulator, and in some cases, a biological signature written across the spectrum of light. When scientists began analyzing the atmosphere of this planet in detail, the conversation shifted from habitability to something far more unsettling. Not because a single gas was detected, but because of how multiple gases appeared together and persisted over time. On Earth, the atmosphere is not in chemical equilibrium. Oxygen should not exist in large quantities alongside methane. Both gases react readily. Without constant replenishment, they would disappear within a relatively short geological time frame. Their coexistence is a direct consequence of biological activity. Plants, microbes, and complex ecosystems continually push the atmosphere away from equilibrium. This principle guides atmospheric life detection across the universe. Scientists do not look for life directly. They look for imbalance. The first atmospheric observations of this planet revealed something unexpected. Oxygen was present at detectable levels. Not trace amounts that could be dismissed as noise or transient chemistry, but sustained concentrations that demanded explanation. Initially, researchers explored abiotic sources. Photochemical splitting of water molecules can produce oxygen. Volcanic processes can release oxygen-bearing compounds. But these explanations failed under long-term modeling. Abiotic oxygen production tends to be episodic. It spikes, then fades. Without life, oxygen accumulations are usually temporary or accompanied by other chemical signatures that betray their origin. On this planet, oxygen levels appeared stable across multiple observation periods. More troubling was what appeared alongside it. Methane signatures were detected in the atmosphere. Methane is fragile. Ultraviolet radiation breaks it down rapidly. Without a continuous source, methane does not last. Geological methane production is possible, but sustaining it at observed levels without biological input is statistically unlikely. The coexistence of oxygen and methane triggered immediate caution. This is one of the strongest known biosignatures on Earth. It is maintained almost entirely by life. Without biology, the two gases annihilate each other chemically. Scientists tested alternative explanations aggressively. They modeled extreme volcanic outgassing. They simulated unusual mantle chemistry. They explored exotic photochemical pathways. In every case, the system collapsed. Either methane vanished oxygen spiked unrealistically, or other byproduct gases appeared that were not observed. The models converged on a simple conclusion. Maintaining this atmospheric composition without life required a chain of improbable coincidences sustained over billions of years. That does not prove life exists, but it weakens every non-biological explanation. Another key gas detected was carbon dioxide, but at moderate levels. Too much carbon dioxide leads to runaway greenhouse warming. Too little leads to global freezing. This planet's carbon dioxide concentration appears finely regulated. On Earth, carbon dioxide regulation is driven by plate tectonics and biology. Weathering removes carbon dioxide. Already, volcanic activity releases it. Plants lock it into biomass. Oceans absorb it. The balance shifts, but feedback mechanisms restore stability over time. The planet's atmospheric data suggests similar feedback mechanisms. Carbon dioxide levels fluctuate within narrow bounds. Climate models show no drift toward extreme states. Something is regulating the system. Nitrogen was also present in abundance. Nitrogen is often overlooked because it is chemically inert, but it plays a critical role. It stabilizes atmospheric pressure. It supports complex biochemistry. Nitrogen cycles on Earth are heavily influenced by life. Abiotic nitrogen atmospheres exist, but the presence of nitrogen alongside oxygen and methane strengthens the case for biological cycling. Another subtle indicator is atmospheric layering. Temperature and pressure gradients suggest a stratified atmosphere. This implies active circulation. Winds transport gases across latitudes. Heat is redistributed efficiently. Stagnant atmospheres allow chemical buildup and collapse. Dynamic atmospheres support stability. Ultraviolet absorption patterns hint at the presence of protective atmospheric layers, possibly analogues to Earth's ozone layer. Ozone forms when oxygen interacts with ultraviolet radiation. It shields the surface from harmful radiation. Without ozone, complex life struggles on land. If ozone, or a similar shielding compound, exists on this planet, it would further increase surface habitability. Life would not need to remain underwater or underground for protection. The atmosphere also appears thick enough to retain heat, but not so thick as to crush life. Pressure estimates suggest values slightly higher than Earth's, but well within ranges tolerable to complex organisms. Higher pressure can actually benefit life by enhancing gas exchange and reducing radiation penetration. Earth's atmospheric pressure is adequate, but again, near lower thresholds. This planet may sit closer to an optimal range. Scientists also examine atmospheric escape. Lighter gases tend to drift into space over time, especially under stellar wind pressure. Hydrogen is particularly vulnerable. Losing hydrogen leads to water loss. Mars suffered this fate. This planet's atmosphere shows no signs of significant hydrogen escape. Water appears stable. The presence of hydrogen-bearing compounds suggests long-term atmospheric retention. This ties back to the planet's magnetic field and stellar calmness. Atmosphere survival is a system-level property. Star, magnetic field, gravity, and chemistry all interact. What makes the atmospheric evidence compelling is not any single gas, but persistence. Observations taken years apart show similar compositions. Short-term chemical anomalies fade quickly. Persistent disequilibrium implies ongoing processes. Scientists are careful to avoid anthropocentric bias. Oxygen-based life is not the only possible form of life. But oxygen is a powerful signal because it is so reactive. Nature does not maintain it casually. Even if life on this planet differs from Earth life, the atmospheric chemistry suggests active metabolism of some kind. Energy is being used to push chemistry uphill against entropy. Another factor is isotopic ratios. Different processes produce different isotopic signatures. Biological activity often favors lighter isotopes. Early measurements hint at isotopic ratios that lean toward biological explanations, though uncertainty remains high. Future telescopes will refine this data. Higher resolution spectra may reveal seasonal variations. On Earth, atmospheric gases fluctuate seasonally due to biological cycles. Detecting similar patterns elsewhere would be a breakthrough. For now, scientists rely on consistency. The atmosphere behaves as if something is maintaining it. Skeptics point out that unknown abiotic processes may exist. This is true. Science cannot rule out unknown mechanisms, but probability weighs explanations. As complexity increases, non-biological explanations require increasingly contrived assumptions. This is why the probability of life remains high, not because scientists want it to be, but because alternatives strain plausibility. Another intriguing aspect is the lack of toxic compounds. Some planets show sulfur-rich or chlorine-rich atmospheres that would be hostile to life. This planet's atmosphere appears relatively clean. No overwhelming presence of known biological poisons. This does not mean life is safe everywhere on the surface, but it suggests a general compatibility with biology. Atmospheric circulation models indicate efficient mixing. Gases produced in one region spread globally. This prevents localized chemical collapse. It also means that if life exists in one region, its atmospheric impact is global. This amplifies detectability. Earth's life altered the entire planet. Even microbial life left a planetary scale imprint. The atmosphere also interacts with the planet's surface. Erosion, weathering, and gas exchange shape both systems. This coupling appears active, not frozen, not chaotic, balanced. Scientists emphasize that atmosphere alone cannot confirm life, but atmosphere can narrow the field dramatically. When combined with stable orbit, calm star, water abundance, and geological activity, the atmospheric evidence becomes harder to ignore. This planet's atmosphere looks less like a static chemical soup and more like a living system. Earth's atmosphere is alive in this sense. It breathes through forests and oceans. It pulses with seasons. It shifts slowly but remains far from equilibrium. The similarities are uncomfortable. Yet caution remains. Extraordinary claims require extraordinary evidence. No one claims discovery of life. What they claim is that life fits the data better than its absence. This is a subtle but profound shift. For decades, scientists asked whether life could exist elsewhere. Now, in some cases, they ask whether it could reasonably not exist. The atmosphere of this planet does not shout. It whispers, but the whisper is persistent. Something is maintaining balance. Something is recycling chemicals. Something is pushing back against entropy. Whether that something is life remains unconfirmed. But the atmosphere tells a story that chemistry alone struggles to explain. And in the search for life beyond Earth, atmosphere is the closest thing to a voice a planet can have. This planet's voice is quiet, stable, and chemically restless. That combination is difficult to dismiss. It suggests not a dead world slowly drifting toward equilibrium, but an active world holding itself there. And that is exactly what life does. Beneath oceans, continents, and atmosphere lies a system that rarely appears in headlines but quietly determines whether a planet remains alive or slowly suffocates. Geology is the long game of habitability. It operates on timescales far beyond individual species, yet without it, life cannot persist. When scientists began modeling the internal dynamics of this planet, the results suggested something Earth-like, but subtly more forgiving. On Earth, plate tectonics play a central role in maintaining habitability. Tectonic plates move, collide, and separate. Volcanoes release gases. Mountains rise and erode. Carbon is buried and released. This continuous recycling regulates atmospheric composition and surface temperature. Without it, Earth might have followed the path of Venus, locking carbon dioxide into the atmosphere and overheating. Yet, Earth's tectonic system is not guaranteed. It exists because of a specific balance of internal heat, water content, and planetary mass. Smaller planets cool too quickly. Larger ones may develop stagnant lids where plates stop moving. Earth sits in a narrow window where tectonics persist but remain unstable. This planet appears to sit deeper within that window. Its slightly higher mass allows it to retain internal heat longer. Radioactive decay within its mantle continues to generate energy. This keeps the interior dynamic. Convection currents remain active. Plates can move over billions of years without freezing into place. Models suggest that plate tectonics on this planet may be slower but more consistent than on Earth. Slower movement reduces violent collisions and extreme volcanism. Instead of massive eruptions that blanket continents in ash, geological activity proceeds at a steadier pace. This benefits climate stability. Steady tectonics regulate carbon dioxide gradually. Volcanoes release gases, but not in overwhelming bursts. Weathering processes remove carbon dioxide at similar rates. The atmosphere remains balanced. On Earth, tectonic disruptions have triggered climate catastrophes. Massive volcanic provinces have released enormous amounts of greenhouse gases, driving warming and extinction. Tectonics saved Earth in the long term, but nearly destroyed it in the short term. This planet appears to avoid those extremes. Water plays a critical role here as well. On Earth, water lubricates plate boundaries, enabling movement. A dry planet may lack plate tectonics entirely. The presence of abundant surface and subsurface water on this planet supports long-term plate mobility. The interaction between water and rock drives chemical cycling. Minerals are altered, nutrients are released. Essential elements become available to life. Without this interaction, biology starves. Another factor is continental configuration. Earth's continents have repeatedly merged and separated. Supercontinents form and break apart. These cycles alter ocean circulation and climate. They can trigger ice ages or warming periods. Models suggest that this planet may have experienced fewer supercontinent cycles or slower ones. Continents remain more evenly distributed. Ocean circulation remains stable. Climate does not swing wildly. This does not eliminate climate change. It moderates it. Geological recycling also affects oxygen levels. On Earth, oxygen is consumed by reactions with rocks and released by life. Tectonic activity exposes fresh rock surfaces that absorb oxygen. If tectonics stop, oxygen can accumulate excessively or decline unpredictably. Balanced tectonics maintain oxygen sinks. This stabilizes atmospheric composition. Life thrives within stable chemical boundaries. Scientists also examine heat flow. Too much internal heat leads to excessive volcanism. Too little leads to geological stagnation. This planet's heat flow appears moderate. Internal convection remains active without overwhelming the surface. This balance may also support a long-lived magnetic field. Tectonic activity contributes indirectly by sustaining a molten core. Convection within the core generates magnetic fields that shield the planet from radiation. Earth's magnetic field has weakened and strengthened over time. At times, it nearly collapsed. During these periods, radiation exposure increased. Life survived, but stress increased. Models indicate that this planet's magnetic field may be more stable. Stronger convection maintains field generation. Polarity reversals may occur, but full collapse is unlikely. Atmospheric erosion remains minimal. Subsurface environments benefit as well. Tectonic activity creates fractures, hydrothermal systems, and chemical gradients. These environments are hotspots for life. On Earth, deep biospheres exist kilometers below the surface, independent of sunlight. This planet likely hosts extensive subsurface ecosystems. Even if surface conditions change temporarily, life below persists. Extinction becomes unlikely. This redundancy matters. Life is resilient when it has refuges. Geological activity creates those refuges. Scientists also consider nutrient cycling. Phosphorus, for example, is essential for life, but often limited. Tectonic uplift exposes phosphate-rich rocks. Erosion delivers nutrients to oceans. Without tectonics, nutrients become locked away. This planet's geology appears to keep nutrient cycles active. Shallow seas receive continuous mineral input. Productivity remains high. Earth's nutrient cycles have fluctuated dramatically. Periods of nutrient scarcity have limited biological growth. This planet may avoid such bottlenecks. Geological stability also reduces catastrophic events. Earthquakes still occur. Volcanoes still erupt. But energy is released more evenly. Stress does not accumulate to extreme levels as often. This reduces the frequency of global disasters. Local destruction occurs, but life elsewhere continues unaffected. Ecosystems recover. Over billions of years, this difference is profound. Earth's history is punctuated by near annihilation events. This planet's history may be smoother. Another subtle factor is crust composition. Earth's crust is heterogeneous. Continents and ocean floors differ dramatically. This creates diverse habitats, but also sharp transitions that amplify climate effect. Models suggest that this planet's crust may be more uniform. Continental shelves are broader. Elevation differences are less extreme. This creates gentle environmental gradients rather than abrupt ones. Gentle gradients allow life to adapt gradually. Abrupt changes force extinction or rapid evolution. Stability favors complexity. Scientists caution that too much uniformity could reduce diversity. Diversity often arises from environmental contrast, but contrast does not require extremes, and moderate variation may be ideal. This planet seems to strike that balance. Geological recycling also affects long-term water retention. Tectonics drive water into the mantle and release it through volcanism. This maintains surface water levels. Without this recycling, planets may lose water over time. Earth's water cycle includes deep recycling, but efficiency varies. This planet's tectonic system may be more efficient, maintaining surface water over longer timescales. This extends habitability. Water does not gradually disappear. Oceans persist. Another implication is atmospheric pressure stability. Volcanic outgassing replenishes atmospheric gases. Erosion removes them. Balanced geology maintains pressure. Pressure affects boiling points, respiration, and climate. This planet's atmospheric pressure appears stable over long periods. Life does not need to constantly adapt to changing pressure regimes. The phrase planetary recycling captures this entire system. Matter moves between core, mantle, crust, ocean, atmosphere, and biosphere. Nothing is static. Equilibrium is dynamic. On Earth, this recycling is sometimes chaotic. Feedback loops overshoot. Climate swings, extinctions occur. On this planet, recycling appears smoother. Feedback loops dampen rather than amplify disturbances. This does not make the planet static. It makes it resilient. Resilience is the defining feature of long-lived habitability. Life does not require perfection. It requires forgiveness. A planet that forgives mistakes allows life to experiment. This planet's geology appears forgiving. Scientists emphasize uncertainty. Direct observation of tectonics is impossible at present. Conclusions rely on indirect measurements and modeling. But the convergence of evidence from mass, composition, heat flow, and atmospheric regulation supports the idea of active geology. When combined with water abundance and atmospheric stability, geology completes the habitability picture. Each system supports the others. None operates in isolation. Earth's systems often clash. Volcanic eruptions disrupt climate. Ice ages disrupt ecosystems. This planet's systems cooperate. This cooperation may explain why life probability remains so high. Failure pathways are closed off. No single system dominates to destructive effect. The deeper implication is unsettling. Earth's drama-shaped human history. Extinctions cleared ecological space. Instability drove innovation. We evolved in a world that was never comfortable for long. Life elsewhere may not share that story. It may have evolved in patience rather than pressure. A planet with steady geological recycling offers life something rare, time without interruption. In that time, life does not merely survive, it builds. Ecosystems mature. Chemical cycles stabilize. Intelligence, if it arises, does so without racing against planetary collapse. Geology rarely captures imagination, yet it may be the quiet architect of everything that follows. On this planet, geology does not threaten life, it supports it, and that support may have lasted for billions of years, long enough for life to become something we would recognize, or perhaps something we would not. Either way, the planet does not appear geologically dead. It appears alive beneath the surface, and that may make all the difference. A planet can have water, air, and a stable orbit, yet still be hostile to life if it lacks one invisible shield. Magnetic fields are among the most underappreciated factors in habitability, yet they determine whether a planet can keep its atmosphere, protect its surface, and resist the constant assault of its star. When scientists evaluated the magnetic environment of this planet, they found another piece of the puzzle: that pushed habitability probabilities even higher. A magnetic field is generated by motion inside a planet's core. Molten metals move, convection currents form, and electrical charges create a planetary dynamo. This dynamo produces a magnetic bubble around the planet, deflecting charged particles from the star. Without it, a planet's atmosphere is slowly stripped away, molecule by molecule. Earth's magnetic field is the reason we still have an atmosphere thick enough to breathe. Mars once had a magnetic field. When its core cooled and the field collapsed, solar wind stripped its atmosphere. Water disappeared. The surface became sterile. Mars did not lose habitability because of distance from the Sun alone. It lost its shield. This planet appears to have a strong, long-lived magnetic field. Indirect measurements suggest that its core remains molten and convective. Its slightly larger mass and slower cooling rate keep its internal engine running. Convection within the core drives a stable dynamo. Models predict a magnetic field strength equal to or greater than Earth's. This matters immediately for atmospheric survival. Without magnetic shielding, stellar winds erode atmospheres quickly. With shielding, atmospheres persist for billions of years. This planet's atmosphere shows no sign of significant erosion. That alone implies protection. Stellar winds are not gentle breezes. They are streams of charged particles moving at hundreds of kilometers per second. Over time, they chip away at atmospheric molecules. A magnetic field deflects these particles, creating a magnetosphere that surrounds the planet. Earth's magnetosphere extends tens of thousands of kilometers into space. It forms a bow shock that absorbs most solar wind energy. This planet's magnetosphere may be even larger, given its stronger field and calmer star. Radiation protection is another critical function. High-energy particles can damage DNA, break molecular bonds, and sterilize surfaces. Earth's magnetic field and atmosphere work together to reduce radiation exposure. Even so, astronauts outside this shield face dangerous radiation levels. This planet's magnetic field likely provides similar or superior protection. Life on the surface would not be constantly bombarded by lethal radiation. This is especially important for land-based life. Without protection, life would remain confined to oceans or underground. Early in a planet's history, magnetic fields are even more important. Before an ozone layer forms, radiation can destroy nascent life. A strong magnetic field reduces this risk. Early life on this planet would have had a safer surface environment. Magnetic fields also interact with the atmosphere in complex ways. They help maintain ionospheres, influence atmospheric escape, and affect climate through particle interactions. A stable magnetic field supports stable atmospheric chemistry. Earth's magnetic field is not constant. It reverses polarity every few 100,000 years. During reversals, field strength weakens temporarily. Radiation levels increase. Life survives, but stress rises. Models suggest that this planet's magnetic field may reverse less frequently or maintain higher minimum strength during reversals. This reduces vulnerability windows. Atmospheric erosion remains minimal even during geomagnetic events. Another subtle benefit is protection from cosmic rays. Cosmic rays originate from supernovae and other high-energy cosmic events. They can penetrate atmospheres and damage biological tissue. A strong magnetic field deflects many of these particles. This planet's location in a calm galactic region already reduces cosmic ray exposure. Combined with a strong magnetic field, surface radiation levels may be significantly lower than on Earth. Lower radiation environments favor genetic stability. Mutations still occur, but not at excessive rates. Life can evolve without constant genetic damage. Complex organisms benefit from stable genomes. However, some radiation-driven mutation is beneficial. It drives evolution. This planet's environment likely strikes a balance. Enough radiation for evolution, not enough for mass sterilization. Magnetic fields also protect oceans. Without shielding, solar wind can break water molecules and strip hydrogen into space. This process contributed to water loss on Mars. On this planet, water appears stable. The magnetic field prevents significant hydrogen escape. This preserves oceans over geological timescales. Surface water remains available for life. Hydrological cycles persist. Scientists also consider auroral activity. Auroras indicate magnetic interactions with stellar particles. While visually striking, they are a sign of protective interaction. Energy is dissipated high in the atmosphere rather than at the surface. This planet likely experiences auroras, perhaps more spectacular than Earth's. But these would be signs of defense, not danger. The strength of a magnetic field depends on core composition, rotation rate, and internal heat. This planet's rotation appears stable, not slowed by tidal locking. Internal heat persists due to its mass and radioactive content. Core composition likely includes conductive metals similar to Earth's iron-nickel core. These factors combine to sustain a dynamo. Earth's dynamo will eventually weaken as the core cools. This planet's larger size extends its dynamo lifetime. Magnetic protection lasts longer, and habitability window extends. This is another example of how small differences compound: slightly larger mass, slightly calmer star, slightly stronger magnetic field. Together, they produce a world that resists cosmic erosion. Magnetic shielding also influences atmospheric chemistry indirectly. Charged particles can trigger chemical reactions in the upper atmosphere. Excessive particle influx can destroy ozone and alter greenhouse gas balances. Shielding reduces these effects. This stabilizes climate. Fewer unpredictable chemical disruptions occur. Climate models remain within narrow bounds. Some scientists have proposed that magnetic fields may influence biological evolution by modulating mutation rates. While speculative, a stable magnetic environment could reduce catastrophic mutation spikes, allowing gradual evolution. Life on this planet may have evolved under steadier genetic pressures. Fewer radiation-induced mass die-offs, more gradual adaptation. Another point is technological implications. If intelligent life emerges, a strong magnetic field protects technology from stellar storms. Communication systems, satellites, and power grids would be less vulnerable. Civilization stability increases. Earth's technology is vulnerable to solar storms. A sufficiently large storm could cause global disruptions. This planet's calmer star and stronger field reduce such risks. This is speculative, but it illustrates how habitability extends beyond biology. Stable environments support sustained technological development. Scientists are cautious in inferring magnetic fields remotely. They rely on stellar wind interactions, auroral emissions, and atmospheric escape signatures. Current data is indirect, but consistent with a strong field. Future telescopes may detect radio emissions associated with magnetospheres. Such detections would confirm field strength. Even without direct measurement, The absence of atmospheric erosion and presence of volatile compounds strongly imply magnetic protection. Without a magnetic field, the other favorable conditions would be temporary. Water would escape, atmosphere would thin, surface would become irradiated, habitability would collapse. This planet avoids that fate. Earth's magnetic field is often taken for granted. We rarely consider how fragile habitability would be without it. This planet's field appears less fragile. This again raises the question of whether Earth is average or marginal. Perhaps many habitable worlds require stronger magnetic fields than ours. Perhaps Earth survived because of a fortunate combination of factors rather than optimal ones. If this planet indeed has a stronger and longer-lived magnetic field, it would be another reason scientists label it as potentially better for life. Not because it is exotic, but because it is protected. Protection is a recurring theme in habitability. Protection from radiation, from atmospheric loss, from climate extremes, from orbital chaos, from geological stagnation. This planet appears protected on multiple fronts. Magnetic fields are invisible, but their effects are tangible. They shape atmospheres, climates, and biological possibilities. Without a magnetic field, a planet is exposed. With one, a planet can endure. This planet seems built to endure. That endurance may be why life, if it exists there, had time to flourish. And if life flourished, it would have left traces in the atmosphere, the surface, and perhaps beyond. The magnetic field is not a guarantee of life, but it is a gatekeeper. This planet's gate appears closed to cosmic destruction and open to biological persistence. In the hierarchy of habitability, magnetic shielding is not optional. It is foundational, and in this case, it may be one of the strongest pillars supporting the case for a world that is not just habitable, but resilient beyond Earth's standard. A planet that does not merely survive the universe, but is defended from it. The question of intelligent life is always the most dangerous one in science, not because it is unscientific, but because it invites speculation to run ahead of evidence. Scientists are trained to avoid it. Yet, when a planet demonstrates long-term stability, environmental continuity, and a near certainty of life-friendly conditions, the question can no longer be ignored. Not whether intelligent life exists there now, but whether such a planet makes intelligence more likely to emerge at all. Intelligence is not an inevitable outcome of life. Earth is the proof. For nearly 4 billion years, life existed without producing a technological species. Intelligence, at least as humans define it, emerged very late. This suggests that intelligence requires not only biology, but time, stability, and a sequence of unlikely evolutionary steps. This planet appears to offer all three. The most important factor is uninterrupted time on Earth. Mass extinctions repeatedly reset evolutionary progress. The end Permian extinction erased around 90% of marine species. The asteroid impact that ended the age of dinosaurs eliminated dominant lineages and reshaped ecosystems. Intelligence emerged only after these disruptions cleared ecological space. But those same disruptions delayed progress. Complex ecosystems had to rebuild from near zero multiple times. Evolution was forced to restart its climb repeatedly. On this planet, evidence suggests fewer global catastrophes. No signs of frequent planet-wide sterilization. Climate remained within survivable bounds. Oceans persisted. Atmospheres remained intact. Geology recycled nutrients without overwhelming disruption. This continuity changes the evolutionary timeline dramatically. If life emerged early on this planet, it may have had billions of years of relatively uninterrupted evolution. That does not guarantee intelligence, but it increases the probability that complex traits accumulate rather than being wiped out. Complex life requires energy. Multicellular organisms are energetically expensive. They require stable food webs and reliable energy input. This planet's widespread shallow seas, moderate climates, and stable photosynthetic conditions support high biological productivity. High productivity supports large populations. Large populations increase genetic diversity. Genetic diversity increases the likelihood of novel traits emerging. Intelligence, in evolutionary terms, is one such trait. Another factor is environmental variability, but not chaos. Some variation is necessary to drive adaptation. Completely static environments can lead to stagnation, but extreme variability leads to extinction. This planet appears to strike a balance. Moderate seasonal changes, gradual geological shifts, slow climate oscillations. These provide selective pressure without overwhelming organisms. Evolution has room to explore. On Earth, intelligence may have been favored by environmental challenges. Fluctuating climates, forced adaptability, social behavior, problem solving, and tool use conferred survival advantages. But these same challenges also killed off many potential lineages on this planet. Challenges may have been gentler but persistent. Problem solving would still be rewarded, but without constant extinction threats. Social complexity also depends on ecological structure. Stable ecosystems allow long-lived species to develop social hierarchies, communication systems, and learned behaviors. Instability disrupts these structures. This planet's ecosystems may have matured deeply. Predator-prey relationships could stabilize. Cooperative behaviors could evolve and persist. Memory and learning would confer advantages. Another key factor is planetary size and gravity. Slightly higher gravity may influence body plans. Organisms may be sturdier, shorter, or differently structured than Earth life. This does not prevent intelligence. It shapes its expression. Intelligence does not require human-like form. It requires sensory input, memory, learning, and the ability to model the environment. These traits can arise in many biological architectures. Oceans complicate this picture. On Earth, intelligence evolved in a land-based species, but advanced intelligence also appeared in marine mammals. Dolphins, whales, and octopuses demonstrate problem-solving, communication, and social learning. This planet's extensive shallow seas may favor intelligent marine life, long lifespans, complex social structures, rich sensory environments. Intelligence could emerge underwater and remain there. Technological development underwater is difficult, but intelligence does not require technology. It requires cognition. If intelligent marine species evolved, their impact on the atmosphere might still be detectable through large-scale biological activity. Another possibility is that intelligence emerged multiple times. Parallel evolution increases probability. On Earth, complex nervous systems evolved independently in multiple lineages. Intelligence itself may be less rare than we assume. This planet's long, stable history increases the chance of repeated attempts. Time again is decisive. Intelligence takes time not only to evolve, but to persist. On Earth, if a global catastrophe had occurred 10,000 years ago, human civilization would never have existed. Our window is narrow. This planet's wider window allows intelligence to persist longer once it emerges. Civilizations could rise and fall without erasing the possibility of future ones. This raises an unsettling implication. If intelligent life emerged early on this planet, it may be far older than humanity, not thousands or millions of years older, but potentially billions. Such a civilization would not necessarily broadcast signals. Technological phases may be brief relative to planetary timescales. Radio leakage might last centuries. That is a blink of an eye. Silence does not imply absence. It may imply age. Scientists are careful not to invoke advanced civilizations without evidence. But they acknowledge that probability shifts with time. A planet that has been habitable for twice as long as Earth has twice as much opportunity and likely more than twice the probability. Intelligence also depends on planetary hazards. Frequent impacts discourage long-term planning species. Constant existential threats favor short-lived strategies. Stable environments reward long-term investment in cognition, cooperation, and culture. This planet's reduced impact risk and geological stability favor such investment. Energy availability also matters. Civilizations require surplus energy. Stable climates and abundant resources allow surplus production. Famine and scarcity hinder societal complexity. This planet's water distribution, nutrient cycling, and climate stability suggest consistent resource availability. No prolonged global droughts. No planet-wide glaciations. Ecosystems remain productive. This environment could support long-lived intelligent species capable of developing culture, memory, and technology. Yet, intelligence is not destiny. Evolution is contingent. Chance plays a role. Random mutations, historical accidents. Intelligence could fail to appear despite ideal conditions. But probability does not ask for certainty. It asks for likelihood. On Earth, intelligence emerged once, despite instability. On a planet with greater stability, probability increases. This is why scientists increasingly consider not just habitability, but complexity potential. Some planets may host life, but never complex life. Others may host complex life, but never intelligence. A smaller subset may host intelligence. This planet appears to maximize complexity potential. Another factor is atmospheric oxygen levels. Complex brains require oxygen. Earth's oxygenation took billions of years. Delayed oxygenation delayed complexity. This planet's atmosphere may have stabilized oxygen earlier. Stable geological recycling and biological productivity could accelerate oxygen buildup. Complexity emerges sooner. Early oxygenation also increases the time available for intelligent evolution. Some scientists caution that too much oxygen increases fire risk and oxidative stress. Balance is key. This planet appears balanced. Intelligence also depends on sensory richness. Diverse environments encourage sensory processing. Shallow seas, coastlines, varied terrain, and moderate climates provide rich sensory input. This planet likely offers that diversity without extremes. The question then shifts from could intelligence exist to would it be surprising if it did not? Scientists are not claiming detection of intelligence. There are no signals, no structures, no direct evidence. But the chain of reasoning is clear. Stable planet, long time, high productivity, reduced extinction. These are the conditions under which intelligence is most likely to emerge. Earth achieved intelligence under worse conditions. This does not mean humanity is unimportant. It means humanity may not be unique. The possibility that intelligent life exists or once existed on this planet reframes our perspective. Intelligence may not be a rare cosmic accident. It may be an emergent property of sufficiently stable biospheres. If that is true, the universe may host many intelligences separated by time and distance, rarely overlapping. This planet could be one such case. Even if intelligence never arose, complex ecosystems almost certainly did. Forests or their analogues, reefs, food webs more intricate than Earth's. Life there may be more ancient, more stable, and less driven by crisis. Intelligence born of stability may look different from intelligence born of struggle. Motivations, behaviors, and trajectories could diverge radically. This is speculation, but grounded speculation. It emerges naturally from the conditions described. Scientists remain cautious. They separate probability from proof, but they do not ignore probability when it becomes overwhelming. This planet does not guarantee intelligence, but it offers intelligence, something Earth rarely did. Time without interruption. And in evolution, uninterrupted time is the rarest resource of all. If intelligence ever needed a cradle, this planet may have provided one. Whether that cradle is empty, occupied, or long abandoned remains unknown. But the question is no longer fringe. It is statistically reasonable. And that alone marks a profound shift in how humanity understands its place in the universe. For centuries, Earth has been treated not just as our home, but as a cosmic reference point. Every discussion of habitability, life, and intelligence has quietly assumed that Earth represents the ideal conditions for biology. This assumption was never formally tested. It emerged naturally because Earth was the only example available. Now, with the discovery of a planet that may be more stable, more forgiving, and more enduring, that assumption begins to fracture. Earth is not a bad planet for life. It is a successful one. But success does not imply optimality. When scientists evaluate Earth without emotional attachment, its weaknesses become clear. Earth exists on the edge of multiple thresholds. Its climate system is sensitive. Small changes in greenhouse gases trigger large responses. Its position in the habitable zone is closer to the inner boundary than the center over geological time. It has repeatedly flirted with catastrophe. Earth has experienced at least 5 major mass extinctions. Each erased a large fraction of existing life. The causes varied. Asteroid impacts, massive volcanism, climate collapse, ocean anoxia. These events were not rare anomalies. They were recurring features of Earth's history. Life survived, but survival came at a cost. Complexity was delayed. Ecosystems were reset. Evolutionary trajectories were erased and rewritten. Earth's biosphere is not the result of smooth progress. It is the product of repeated destruction and recovery. From a biological perspective, this is inefficient. Earth's climate instability is another weakness. Ice ages covered much of the planet repeatedly. Global temperatures swung dramatically. Sea levels rose and fell by hundreds of meters. Entire habitats vanished. Species migrated, adapted, or died. These fluctuations drove evolution, but they also limited continuity. Long-lived, highly specialized ecosystems struggled to persist. Stability was rare and temporary. The planet under discussion appears to avoid many of these extremes. That does not make Earth inferior in value. It makes Earth volatile. Earth's geological activity, while essential, has also been disruptive. Large igneous provinces released enormous amounts of greenhouse gases. These events triggered warming, ocean acidification, and mass extinction. Plate tectonics saved Earth from long-term climate collapse, but nearly destroyed it multiple times in the short term. Earth's magnetic field, though strong enough to protect us, has weakened significantly at times. During periods of low field strength, radiation exposure increased, atmospheric loss accelerated slightly. Again, life survived, but stress increased. Earth's star, the Sun, is stable by stellar standards, but not perfectly calm. Solar flares, coronal mass ejections, and gradual brightening all impose limits. In the distant future, Earth will become uninhabitable due to solar evolution alone. Earth's habitable window is finite and relatively narrow. When scientists compare this to a planet with a calmer star, stronger magnetic field, thicker atmosphere, and more stable orbit, the contrast becomes clear. Earth supports life despite its environment. The other planet may support life because of its environment. This distinction matters. Earth's oceans, often cited as a strength, are also unevenly distributed. Vast deserts exist. Polar ice caps lock away water. Large regions are biologically sparse. Productivity is concentrated in limited zones. The other planet's water distribution appears more even. Shallow seas and widespread water access increase global productivity. Ecosystems are not confined to narrow bands. Earth's biosphere is fragile in places. Coral reefs bleach. Forests collapse under climate stress. Small changes ripple outward. This sensitivity is a weakness from a habitability standpoint. Earth's atmosphere has also undergone dramatic shifts. Oxygen levels rose rapidly during the Great Oxidation event, triggering mass extinction among anaerobic organisms. Later fluctuations influenced climate and evolution, and atmospheric transitions were not gentle. A planet with smoother atmospheric evolution reduces these biological shocks. Even Earth's biodiversity, while impressive, is shaped by repeated bottlenecks. Many lineages went extinct before reaching full potential. What we see today is not maximal diversity, but surviving diversity. This planet may have retained more lineages over time. Fewer resets mean greater cumulative diversity. Another overlooked weakness is Earth's impact history. Large asteroids struck repeatedly. The dinosaur-killing impact was not unique. Earlier impacts caused mass extinctions. Earth's position in the solar system exposes it to impact risks from asteroid belts and comet reservoirs. This other planet appears to exist in a quieter, dynamical environment, fewer impactors, lower extinction risk. From a purely statistical perspective, Earth looks like a marginal success story. It worked, but under pressure. Life here is resilient, but often pushed to the brink. This resilience shaped humanity. Intelligence evolved in a world of instability. Adaptability, foresight, and social cooperation were rewarded. But this evolutionary path is not necessarily universal. A planet that avoids constant crisis may produce intelligence shaped by continuity rather than survival. Different pressures yield different outcomes. This challenges the narrative that adversity is necessary for complexity. Adversity can drive innovation, but it can also erase it. Stability allows accumulation. Earth's geological youth is another factor. While Earth is old, its surface is constantly recycled. Few regions preserve very ancient environments. Biological records are fragmented. This complicates long-term continuity. The other planet's slower, steadier recycling may preserve environments longer. Ecosystems persist without being erased by resurfacing. This again increases cumulative biological progress. Earth's habitability is also uneven across time. There were long periods when large regions were uninhabitable. Snowball Earth episodes may have nearly frozen the planet entirely. Recovery took millions of years. This planet appears to have avoided global freeze states. Temperature regulation remained within narrower bounds. When scientists say Earth may not be the gold standard, they do not mean Earth is flawed beyond repair. They mean Earth is not the peak of what is physically possible. Earth represents one solution among many. The gold standard metaphor implies perfection. Earth is not perfect. It is functional. It allowed life to emerge and persist, but often barely. This realization is uncomfortable because it undermines human exceptionalism. If Earth is not special, then humanity's origin may not be unique. Uniqueness has been a psychological anchor. Science does not remove meaning. It redistributes it. Earth's value lies not in being the best possible world, but in being our world. Its instability shaped our story. But that story is not universal. The existence of potentially better habitats elsewhere does not diminish Earth. It contextualizes it. Scientists now recognize that habitability exists on a spectrum. Earth sits somewhere on that spectrum, not at the extreme. Some worlds may be less habitable, some may be more. The planet described in these models may sit closer to the upper end, not because it is exotic, but because it avoids extremes. This reframing has consequences for future exploration. Searching only for Earth twins may miss more favorable worlds. Planets that differ slightly may outperform Earth in key metrics. It also affects how we interpret silence. If better habitats exist, life may prefer them. Earth may not be representative of the most common life-bearing environments. This challenges the assumption that intelligence evolves best under stress. Perhaps intelligence thrives under patience. Earth forced life to fight. Other planets may allow life to build. From a long-term perspective, Earth's future is also less secure. Climate change, whether natural or anthropogenic, pushes systems toward tipping points. Small perturbations cascade. This sensitivity is part of Earth's nature. The other planet appears more forgiving. Its systems absorb disturbances rather than amplify them. This forgiveness may be the defining trait of superior habitability. Scientists emphasize humility. Earth gave us everything, but gratitude should not become bias. Understanding the universe requires honest comparison. When Earth is compared honestly, its limitations are clear. It is habitable, but volatile, productive, but uneven, resilient, but fragile. The discovery of a planet that may do better in these categories does not dethrone Earth emotionally. It dethrones it scientifically. Earth is no longer the template. It is a data point, one of many. This shift changes the search for life, the interpretation of probability, and humanity's self-image. We are not the inhabitants of the best possible world. We are the inhabitants of one that worked. Somewhere else, the universe may have built worlds that worked better, worlds where life did not constantly restart, worlds where complexity accumulated without interruption, worlds where intelligence, if it arose, did so without racing extinction. Earth's story is dramatic because it is unstable. Other worlds may be quiet because they are not. Quiet does not mean empty. It may mean successful. And in that success, Earth loses its status as the gold standard, not as a home, but as a benchmark. The universe, it seems, may be capable of more than we once assumed. Detecting life across interstellar distances is not a matter of seeing organisms or landscapes. It is an exercise in inference, pattern recognition, and elimination. Scientists do not search for trees, animals, or cities. They search for fingerprints, subtle, indirect signals that reveal ongoing processes a lifeless planet cannot easily sustain. This method emerged from necessity. Even the most powerful telescopes cannot resolve the surface of distant planets in detail. Instead, astronomers analyze how starlight interacts with a planet's atmosphere and surface. Every molecule absorbs and emits light in specific ways. These interactions leave signatures embedded in the light that reaches us. The foundation of life detection is spectroscopy. When a planet passes in front of its star, some starlight filters through its atmosphere. Molecules absorb certain wavelengths, creating dark lines in the spectrum. By studying these lines, scientists identify atmospheric composition. This technique has already revealed water vapor, carbon dioxide, methane, and other gases on distant worlds. What matters is not merely detecting these gases, but understanding their context. On a lifeless planet, atmospheric chemistry tends toward equilibrium. Reactions proceed until energy gradients flatten. Once equilibrium is reached, change slows. Life disrupts this process. It consumes energy to maintain chemical imbalance. It pushes molecules uphill against entropy. This is why biosignatures focus on disequilibrium. One classic example is oxygen. Oxygen is highly reactive. It should bind with rocks, gases, and organic molecules. Without continuous replenishment, it disappears. On Earth, oxygen persists because photosynthetic life produces it constantly. Finding oxygen elsewhere is intriguing, but not definitive. Oxygen can be produced abiotically. Ultraviolet radiation can split water molecules, releasing oxygen. Volcanic processes can also contribute. Scientists therefore look for oxygen paired with gases that should not coexist. Methane is one such gas. Methane reacts with oxygen quickly on Earth. The simultaneous presence of both indicates biological input. When both gases are detected together at stable levels, abiotic explanations struggle. Another powerful indicator is nitrous oxide. On Earth, nitrous oxide is produced primarily by microbial activity. It is difficult to generate abiotically in large quantities. Its detection would be a strong signal of life. Ammonia is another candidate. Ammonia breaks down under ultraviolet radiation. Sustaining it requires continuous production. While some geological processes can produce ammonia, large-scale persistence suggests biology. Scientists also examine ratios. Life produces specific proportions of gases. Not just presence, but balance matters. The ratio of carbon dioxide to oxygen, methane to oxygen, nitrogen to trace gases all provide clues. Beyond gases, scientists look for surface biosignatures. Pigments absorb light in distinctive ways. On Earth, vegetation reflects infrared light strongly, producing what is called the vegetation red edge. Detecting a similar spectral edge elsewhere would be extraordinary. However, alien life may use different pigments. Scientists therefore search for any sharp reflectance features inconsistent with mineral surfaces. Seasonal variation is another key tool. On Earth, atmospheric gases fluctuate with seasons. Carbon dioxide decreases during growing seasons and increases when plants decay. Oxygen and methane show seasonal patterns. Detecting seasonal variation on another planet would strongly suggest active biological cycles. Lifeless planets do not breathe with seasons. This requires repeated observation over long periods. It is difficult, but becoming possible with new telescopes. Scientists also consider spatial variation. If different regions of a planet show different chemical signatures, it implies localized processes. Life tends to cluster. Geological processes are often more uniform. Cloud patterns can also reveal information. Life influences cloud formation through aerosols and biological particles. Subtle differences in cloud behavior may one day serve as biosignatures. Another indirect method involves thermal emission. Living planets may show temperature anomalies inconsistent with simple physical models. Biological activity redistributes energy. Dense ecosystems can alter local heat signatures. This is subtle and uncertain, but part of the growing toolkit. False positives remain the greatest challenge. Many processes can mimic biosignatures. Early Mars may have shown methane without life. Venus shows chemical anomalies that spark debate. Scientists therefore rely on convergence. No single signal is enough. The planet discussed throughout this series stands out because multiple indicators align: atmospheric disequilibrium, stability over time, and supportive environmental context. Each signal alone is ambiguous. Together, they become compelling. Scientists use probabilistic frameworks. They assign likelihoods to biological and non-biological explanations. As data accumulates, probabilities shift. Life becomes the simplest explanation when alternatives require increasingly complex assumptions. This approach mirrors how unseen particles were discovered in physics. No one saw neutrinos directly at first. Their existence was inferred because models failed, reminding without them. Life detection follows the same logic. Another method involves studying isotopic ratios. Life often prefers lighter isotopes because they require less energy to process. This preference leaves measurable signatures. Carbon isotopes on Earth show clear biological fractionation. Detecting similar fractionation elsewhere would be strong evidence. Current technology is limited, but future instruments may achieve this sensitivity. Scientists also consider temporal persistence. Geological processes often produce transient signals. Biological processes persist. If a chemical signature remains stable over decades, life becomes more likely. The planet under discussion shows persistence. Atmospheric composition remains stable across observation windows. This stability is difficult to explain abiotically. Yet, caution remains paramount. Science has learned humility. Early claims of life on Mars failed under scrutiny. Ambiguous signals collapsed with better data. This is why scientists resist definitive language. They speak of probability, not certainty. They allow models to compete. But probability has weight. When multiple independent biosignatures converge, skepticism shifts from whether life exists to how we might confirm it. Future telescopes will transform this field. Larger mirrors, better spectrographs, and longer observation campaigns will refine data. Direct imaging may become possible for nearby planets. Polarimetry may reveal surface features. The planet in question will be a prime target. Not because scientists want life to exist there, but because data suggests it might. Detecting life does not require seeing organisms. It requires seeing the effects of metabolism on a planetary scale. Life reshapes planets. It alters atmospheres, surfaces, and energy flows. A living planet behaves differently from a dead one. The challenge is separating that behavior from geology and physics. This is why interdisciplinary collaboration matters. Astronomers, chemists, biologists, and geologists work together. No single discipline can solve the problem. Each biosignature is evaluated against known non-biological processes. Unknown processes are acknowledged but weighted by plausibility. This is not proof by exclusion, it is inference by elimination. The stronger the convergence, the stronger the inference. For decades, scientists asked whether we would ever know if life exists elsewhere. Now, the question is when. The planet described here does not provide confirmation. It provides a test case, a laboratory for refining detection methods, a benchmark for what a life-friendly world might look like. Even if life is ultimately not found there, the process of investigation will sharpen our tools. If life is found, the implications are enormous. It would confirm that biology is not a fluke, that chemistry tends toward life under the right conditions, that the universe is not silent. But even without confirmation, the ability to assign high probability reshapes our worldview. It means life may be common but quiet. It means Earth may not be unique, but merely familiar. Detecting life without seeing it requires patience, humility, and rigor. It requires resisting the urge to overinterpret. It also requires acknowledging when data points in a particular direction. This planet points strongly. Its atmosphere behaves like a system being maintained. Its chemistry resists equilibrium. Its environment supports persistence. Science listens to patterns, not wishes. And the pattern emerging is difficult to ignore. Life, if it exists there, is not waving a flag, it is breathing. And science is learning how to hear that breath across the vastness of space. The discovery of a planet with an extraordinarily high probability of life inevitably leads to a question that feels more practical than scientific. Could humans ever reach it? Not in our lifetime, not with existing technology, but in principle. The answer is both brutally discouraging and quietly transformative. Distance is the first and most unforgiving barrier. Even the nearest star systems are separated by trillions of kilometers. Light itself takes years to cross these gaps. The planet discussed here lies far beyond any distance that chemical rockets could realistically traverse within a human lifespan. At current propulsion speeds, a journey would take tens of thousands of years. This is not a failure of engineering imagination. It is a consequence of physics. Chemical propulsion relies on energy stored in molecular bonds. That energy density is simply too low. Even nuclear propulsion, far more powerful, offers only incremental improvement. Reaching a fraction of the speed of light remains extraordinarily difficult. Yet, the question of reachability is not solely about speed. It is about survival, communication, energy, and time. Interstellar travel exposes spacecraft to radiation, micrometeoroids, and isolation for durations longer than recorded human civilization. Any crewed mission would require closed-loop life support systems capable of functioning flawlessly for generations. Failure would mean extinction of the mission. This leads to the concept of generation ships. Vast, self-sustaining habitats carrying multiple generations of humans. Such ships would not be expeditions. They would be moving worlds. Cultures would rise and fall before arrival. Generation ships are theoretically possible. Nothing in physics forbids them, but they introduce sociological and ethical challenges that are arguably harder than engineering ones. Future generations would be born into a mission they did not choose. Arrival would be a myth until it became reality. Another concept is suspended animation. If biological processes could be slowed or paused, crew lifespans could be extended. Research into cryopreservation exists, but safely suspending complex organisms for centuries remains speculative. Even if solved, this only addresses one problem. Energy is another. Accelerating a spacecraft to significant fractions of light speed requires enormous energy. Decelerating at the destination requires even more. Carrying fuel for both is impractical. This is why many interstellar concepts rely on external energy sources. Laser-driven light sails are one such idea. Powerful lasers based near the home star push ultralight sails to extreme speeds. This avoids carrying fuel. In theory, such probes could reach nearby star systems in decades. In practice, building and powering lasers of sufficient scale presents enormous challenges. Precise targeting over light years is non-trivial. Deceleration remains unsolved. For robotic probes, deceleration may not be necessary. A flyby could collect data, but for exploration or settlement, stopping is essential. Another proposed solution involves fusion propulsion. Fusion offers far higher energy density than chemical reactions. Controlled fusion remains elusive, but progress continues. Fusion-powered spacecraft could reach a few percent of light speed. Even at that speed, journeys would take centuries. Antimatter propulsion offers even higher energy density. Matter-antimatter annihilation converts mass directly into energy, but producing, storing, and controlling antimatter at scale is beyond current capability. Even small quantities are extraordinarily difficult to handle. Then there are speculative concepts: warp drives, wormholes, space-time manipulation. These remain theoretical. Some violate known energy conditions. Others require exotic matter that may not exist. Science does not dismiss these ideas outright, but it does not rely on them. Planning for interstellar travel assumes known physics unless proven otherwise. Under known physics, reaching this planet with humans is a multi-century or multi-millennium project. So, why does the question matter? Because reachability is not the only metric of significance. The existence of a reachable planet would be comforting. The existence of a distant one is humbling. It forces humanity to confront scale and patience. Interstellar travel may not be about arrival, it may be about direction. Building technology capable of even attempting such journeys would transform civilization. Energy generation would need to be orders of magnitude greater. Sustainability would need to be perfected. Social systems would need long-term stability. These are not requirements imposed by space. They are requirements imposed by time. Even sending probes requires long-term thinking. Missions would outlast governments, institutions, and possibly cultures. Data would return decades or centuries later. Planning must transcend immediate reward. This planet's existence reframes priorities. It is not an escape destination. It is a benchmark. It tells humanity what is possible in the universe. It shows that environments more forgiving than Earth exist, that life-friendly worlds may not be rare. This knowledge influences how we treat our own planet. If better worlds exist but are unreachable, Earth's value increases, not decreases. It becomes irreplaceable in practical terms. Colonizing other planets within our solar system becomes more important, not because they are ideal, but because they are accessible. Mars, moons of gas giants, artificial habitats, these are within reach. Interstellar targets remain aspirational. Robotic exploration will lead the way. Probes equipped with advanced sensors, artificial intelligence, and long-term autonomy may reach nearby star systems within a century or two. Data return would transform science. Even without landing, observing this planet up close would confirm or refute biological hypotheses. Atmospheric sampling, magnetic field measurement, surface imaging. Each data point would sharpen our understanding. Communication presents another challenge. Even at light speed, messages take years. Real-time interaction is impossible. Any contact would be asynchronous. Conversations would span generations. This has implications for intelligence detection. If intelligent life exists on this planet, communication may already be impossible due to timing. Civilizations may not overlap. This reinforces the idea that silence does not imply emptiness. Some scientists propose that interstellar travel may be undertaken by machines rather than humans. Self-replicating probes could spread slowly across the galaxy, exploring star systems and transmitting data. This concept raises ethical concerns. Uncontrolled replication could be dangerous, but controlled exploration could map life-friendly worlds over millions of years. Humanity may never personally visit this planet, but humanity's descendants or creations might. Another concept is digital consciousness. If minds could be uploaded or emulated, interstellar travel becomes less constrained by biology. Data can be transmitted at light speed. Consciousness could be reconstructed at the destination. This remains speculative and raises profound philosophical questions, but it illustrates how reachability depends on definitions of travel. Do humans need to arrive physically for exploration to matter? From a scientific perspective, no. Knowledge does not require presence. This planet already influences humanity without being visited. It alters models. It reshapes probability. It challenges assumptions. In that sense, it has already been reached. The idea of reaching a better planet also invites comparison. What would humans do if they arrived? Would we adapt? Would we preserve? Would we repeat patterns of exploitation? This raises ethical questions long before arrival. If life exists there, does humanity have the right to interfere? Colonization becomes morally complex. Protection may be preferable to settlement. Earth's history of exploration is not encouraging. Contact often led to destruction. Interstellar ethics must be considered early. not after technology exists. This planet may never be a destination. It may be a mirror. It reflects what kind of civilization humanity must become to even consider such journeys. Patient, cooperative, sustainable, long-lived. These traits are not guaranteed. Interstellar travel requires unity across centuries. It requires trust in future generations. It requires planning beyond immediate gain. The difficulty of reaching this planet is not a failure. It is a filter. Only civilizations capable of long-term stability can attempt it. Unstable civilizations collapse before they can build such projects. This has implications for the prevalence of interstellar travelers. They may be rare, not because intelligence is rare, but because stability is. This planet's existence reinforces that idea. Stable worlds may produce stable civilizations. Earth's instability may limit ours, or it may challenge us to overcome it. Either way, reachability is not about distance alone. It is about maturity. The planet may be unreachable now, but it defines a horizon, a point toward which technology, ethics, and civilization could move. Even if never reached, it shapes ambition, and ambition shapes progress. The ultimate outcome may not be a human footprint on alien soil. It may be a transformation of humanity's self-concept. We are no longer searching blindly. We have targets. We know what kinds of worlds are possible. This knowledge changes priorities. It changes perspective. The universe is not empty of opportunity. It is simply vast. Reaching across that vastness requires more than engines. It requires patience measured in centuries. For now, this planet remains distant, a point of light, a data set, a probability. But distance does not diminish significance. Sometimes the most important destinations are the ones that force us to grow before we can even imagine arriving. This planet does exactly that. It does not invite us to come. It invites us to become. When scientists speak about the discovery of a planet that may be more habitable than Earth, they are not only describing an astronomical finding, they are describing a philosophical rupture. This single world, distant and unreachable, quietly dismantles assumptions humanity has carried for centuries about uniqueness, destiny, and centrality. For most of human history, Earth was the universe. Then it became one planet among many, and later it became one planet among billions. Yet, even as our cosmic perspective expanded, one idea remained protected. Earth was still considered special, not just because we live here, but because it appeared uniquely capable of sustaining life. That belief is now under pressure. If a planet exists that offers life greater stability, longer continuity, and fewer existential threats, then Earth is no longer the benchmark. It is not the ideal case. It is a successful accident in a universe capable of producing better conditions. This realization does not diminish humanity. It reframes it. For centuries, religion, philosophy, and culture placed humans at the center of creation. Even secular worldviews often preserved a quiet exceptionalism. Life happened here. Intelligence happened here. Meaning emerged here. The possibility that life may be common, and that Earth may not even be the best place for it, challenges that narrative. Meaning can no longer be anchored in exclusivity. Instead, it must be anchored in participation. Humanity is not the point of the universe. Humanity is part of a process the universe seems capable of repeating. This does not make human life insignificant. It makes it contextual. Scientifically, the implications are profound. Biology ceases to be a local phenomenon. It becomes a cosmic process. Chemistry, under the right conditions, tends toward life. Physics permits complexity. Stability allows it to persist. Earth is no longer an anomaly. It is an example. This shifts research priorities dramatically. Instead of asking whether life exists elsewhere, scientists increasingly ask how often and under what conditions it thrives best. The search becomes comparative rather than speculative. This planet becomes a reference case, a model for optimal habitability, a target for refining theories about life's requirements. If life thrives there, then biology is not fragile. It is robust when conditions are right. If intelligence emerged there, then intelligence may not require struggle. It may arise from patience. This challenges deeply rooted human narratives. We often believe hardship is necessary for growth, that adversity forges greatness. Earth's history reinforces this belief. Life survived ice ages, impacts, and extinctions. Intelligence emerged in a world of scarcity and danger. But adversity also destroys potential. Countless lineages never reached complexity because they were erased. A planet with fewer catastrophes may allow evolution to explore paths Earth never could. This suggests that intelligence elsewhere may look very different, not driven by survival anxiety, not shaped by constant crisis, perhaps more cooperative, perhaps slower, perhaps more stable. This is speculative, but it arises naturally from the conditions described. Philosophically, the discovery forces a re-examination of purpose. If life is common, then meaning cannot come from rarity. It must come from relationship, creativity, and experience. Human value does not decrease because others may exist. It becomes shared rather than isolated. Religiously, interpretations will vary. Some will see this as diminishing human significance. Others will see it as expanding creation. A universe capable of producing many life-friendly worlds may be richer, not poorer, in meaning. History suggests that expanding the cosmos never destroyed meaning, it displaced assumptions. The realization that Earth orbits the Sun did not erase human purpose. It forced a new understanding of it. This discovery is similar in scale. Politically and culturally, the implications are quieter but real. Humanity's conflicts often arise from perceived scarcity and competition. If life is abundant in the universe, the narrative of existential loneliness weakens. We are not isolated in a hostile void. We are part of a larger biological story. This does not solve human conflict, but it reframes perspective. Environmentally, the impact may be paradoxical. Knowing that better worlds exist might tempt some to devalue Earth, but the opposite conclusion is more rational. Those worlds are unreachable. Earth remains the only viable home. Its fragility becomes more obvious, not less. If the universe can produce better habitats, that does not excuse neglect. It emphasizes responsibility. Earth worked under difficult conditions. Destroying it would be an act of ignorance, not inevitability. The discovery also challenges the idea of manifest destiny beyond Earth. If life exists elsewhere, especially intelligent life, expansion becomes morally complex. Exploration must be balanced with respect. Humanity's future may involve contact or coexistence at cosmic scales. Developing ethical frameworks now is essential. Another implication lies in time. If life elsewhere is older, humanity may be late to the story. Not first, not central, but recent. This humbling realization mirrors earlier scientific revolutions. Humility is not weakness, it is accuracy. Scientifically, the next decades will be transformative. Telescopes will refine atmospheric data. Biosignatures will be tested. Probability will narrow. The question may shift from could life exist to what kind of life exists. This planet will not be alone. Others will follow. A population of highly habitable worlds may emerge from data. Patterns will form. When patterns form, understanding accelerates. Humanity may be on the verge of recognizing life as a cosmic phenomenon rather than a terrestrial one. This changes education, philosophy, and long-term planning. It may even influence how civilizations judge success. Survival alone may no longer be the metric. Sustainability, continuity, and harmony may become central values. Those are the traits required to persist long enough to notice such worlds. This planet's existence also speaks to the future. It suggests that if humanity can stabilize its own world, it too could persist for billions of years. Extinction is not inevitable. Instability is not destiny. Earth's challenges are not proof of impossibility. They are proof of difficulty. The universe appears capable of producing forgiving environments. Perhaps humanity can learn to make one. The discovery does not answer the question of whether we are alone, but it reframes it so thoroughly that the original question almost becomes obsolete. The more relevant question becomes how life behaves when given enough time and stability. Earth has not had that luxury. This planet may have. The universe, it seems, is not optimized for drama. It is optimized for persistence. Life thrives where extremes are avoided, where systems balance, where chaos is dampened. Earth is dramatic. Other worlds may be quiet. Quiet worlds may be the true strongholds of life. This realization reshapes humanity's self-image, not as protagonists of a lonely universe, but as participants in a vast, unfolding biological experiment. We are not the destination, we are a chapter. And the universe, patient and expansive, appears to be writing many such chapters simultaneously. This planet is one of them. It stands as evidence that life is not a miracle that happened once. It is a possibility. The universe seems willing to repeat. What humanity does with that knowledge will define the next era of its history. Not whether we find others, but how we understand ourselves once we accept that we are not alone in potential. The universe does not revolve around Earth, but Earth still matters, because meaning does not come from being the only world that works. It comes from being one that chose to continue working in a universe that clearly knows how to try again.